Most of the time, we spend most of our energy and effort focusing on this part of the corn plant. But we're learning as we go. There's a whole lot to be learned and understood from here down. That's what we're going to talk about today. You know, foundations are really important. If you built this building, you can make millions of dollars by charging tourists to come look at your poor foundation. But I'm guessing you're not going to make a lot of money inviting people to come look at your corn that's leaning over, okay? So we want to talk a little bit about roots today. We want to understand, what do we think we know about roots? And the most important word in that sentence is think. Because as we go along, people ask us as we're starting to do this root research, what have you learned about roots? And my number one answer is, we have a lot to learn about roots. That's my answer to the question. We're learning as we go. We'll talk a little bit about root-nutrient interactions, what we know about that. We'll talk about what we've learned in our Practical Farm Research program, and then we'll talk about kind of next steps, what we're going to do next. So how many root systems are there? How many root types are there? We can debate this. For simplicity, I'm going to say there's two, right? There's a fibrous root system and a taproot system. Now, there are also root systems that store nutrients, but they're technically taproot. So a sugar beet, a carrot, that's a taproot that stores carbohydrates as well. But for the most part, we're going to say there's two. So what do? Well, they will take up water and nutrients. They will store carbohydrates. They can be storage. They're structural support. So we know that, obviously. And then the last thing that roots do is they can propagate a plant. So Johnson grass is one of our enemies. Johnson grass produces rhizomes, so rhizomes and stolons can actually propagate a plant if you chop it up. So those are really the four main functions of roots. So how many root systems on a corn plant? A lot of folks would say three, but really there's two. There's a seminal root system and then the nodal root system. So there's two roots. So brace roots are part of the nodal root system. That corn plant will rely on that seminal root system up until that V3, V4 stage, and then it transitions over into the nodal roots. Oftentimes, this is what we call that ugly corn stage. Oftentimes, when we get that ugly corn, that means there's something going on below the ground as we transition from that seminal root system into that nodal root system. Could be a disease, could be a nutrient deficiency, could be soil density issues. But oftentimes when we go into that ugly corn syndrome, it has something to do with that transition from seminal roots to nodal roots. So what do we think we know about roots? Well, roots grow around 2 3/4 inch for every leaf stage. 2 3/4 inches for every leaf stage. Now we know we get a leaf about every 2.5 days. So in essence, we get about an inch of root growth every day. That's pretty interesting. Now we also know that root growth is slower early because of cooler soil temperatures and then really picks up after that V5 growth stage. So technically, roots are growing more than an inch a day after that V5 growth stage, very rapidly. We also know that they stop at flowering. So why does a corn plant stop growing roots at flowering? Because God designed it pretty cool. That corn plant understands it needs to start putting nutrients into the ear. So it's going to stop putting nutrients into the roots and growing roots. We know that roots intercept 1 to 2% of soil by volume, and I'll talk a little bit about that later when we talk about root-nutrient interactions. And then the other thing we know is that roots are a sink. Okay, there is some thought out there, there are some physiologists that will say that there is an inverse correlation between root volume and yield. So think about that for a minute, because that corn plant is putting carbohydrates into the roots. So is there a tipping point where we can actually spend too much energy growing roots as opposed to storing it in the stalk or putting it into the ear? That's something I think we need to learn. Something else we know that for the most part, phosphorus and nitrogen tend to promote root growth, okay? In the presence of phosphorus and nitrogen, roots will proliferate. So this is actually a page out of my son's plant physiology book in school. And if you look in the upper left, that's the control. Look between the two black lines. Because between those two black lines, you'll see they applied nitrate, ammonium, potassium, and then also phosphorus fertility. And what you see is roots tend to proliferate in the presence of phosphorus and nitrogen. That's important. We'll talk about why. So how do nutrients get into the plant? Really, it's one of three ways. It's root interception, mass flow, and diffusion. Let's talk a little bit about those because it will really tie into what we're doing to understand roots a little bit later. So root interception, what is it? So that's the process by which roots grow through the soil, and as they grow through the soil, they kind of bump into a nutrient in the soil. It's really dependent on the root volume in your soil. But root interception, for the most part, is a very minor way for nutrient uptake for most nutrients. Okay, calcium could be an example where root interception can be a major pathway because there's so much calcium in your soils. But let's do some calculations. I'm going to refer to a chart from Barber, okay? And what I want you to look at is that column over on the right. So that column over on the right is pounds per acre. So let's do some math to figure out how do we calculate this root interception. Well, it's really not that hard. So let's say we have 200 pounds of nitrogen in our soil profile. If my roots come in contact with 1 to 2% of soil by volume, then how many pounds of nitrogen are they picking up by root interception? It's basically take 2%, let's say it's 2% root interception, and 200 pounds of nitrogen, take 2% of 200, it's 4 pounds. So root interception, for the most part, is not a major method of uptake for most nutrients. It's really not, because roots just don't intercept as much soil as we think. How about mass flow? Okay, so mass flow, I have a picture of a straw up here. So that plant, in essence, is a great big straw in the field. So as that plant transpires, on a hot day like today, it's transpiring and it's losing moisture. When it does that, it creates a pressure gradient. And that pressure gradient starts moving water through the plant, through the roots, and down in the roots, that pressure gradient starts pulling water through the soil into the plant. That's mass flow, right? So the amount transported to the plant via mass flow depends on a number of things. It depends, for instance, on the amount of water in your soil. It also depends on that gradient pathway to your root. And then it also depends on the concentration of the nutrient in your soil. Think of it this way. Let's say you like to drink your bourbon neat. Okay, that's a very concentrated drink. But let's say you take your bourbon and you mix it with water and ice or Coke or whatever. You dilute that drink. So it takes you more of those, right, to get the same effect from just drinking your bourbon with nothing. That's the stiffness of the drink. Likewise, the soil water has a certain concentration, right, or stiffness of that drink that corn plant takes up. And it's very, very important as we think about mass flow. Now, the other thing I would tell you when we think about mass flow, we're really focused on those nutrients, basically nitrates, borates, sulfates, and chloride, because all those nutrients carry a negative charge. Your soil has a negative charge, so they move very freely in soil water. So mass flow is very important for nitrates, borates, sulfates, chloride as well. So how do we do the calculation as it relates to mass flow? Now we're going to go to that middle column from Barber, okay? And now we're talking about that concentration, the stiffness of that drink, right? So we're going to look at, let's say, for example, we're going to use around 37 parts per million nitrogen. So how do we do the math? Well, I'm going to use an example. I'm going to say that an average corn crop needs 13 inches of water to produce that corn crop, okay? We know that 1 acre inch of water weighs around is around 27,000 gallons. And we know that a gallon of water weighs around 8.3 pounds, right? So basically you multiply those things out, and what you find is that corn crop took up around 2.9 million pounds of water. So then to calculate this mass flow, what you do is you take, back to that chart, remember I said 37 parts per million of nitrates or nitrogen in the soil. Take 37 parts per million times 2.9 million pounds of water, and you come up with 107 pounds of nitrogen that came to that plant via mass flow. You can see that's the majority of nutrient uptake for, again, boron, right, sulfur, nitrogen, and chloride. They move very rapidly in the soil water through mass flow. The other thing I would say, you can you can manipulate this equation, right? You can increase the stiffness of the drink by the placement of the nitrogen, right? The rate of nitrogen. There are a number of things you can do to increase the parts per million in that soil water. All right, let's talk about diffusion then. So think about your high school class. When you dropped a drop of ink in water, it diffused. It went from an area of high concentration out to an area of lower concentration. That's what diffusion is. What happens is in soil is that root grows through the soil. The corn plant will say, I'd like a little phosphorus today. And so that corn sends out signals and root exudates, and the corn plant takes up some phosphorus. And when it does that, right around the root, that area of the root has a lower concentration. And so the nutrient further away starts diffusing across, all right, that soil into that area of low concentration from the area of high concentration. Here's the thing though, diffusion is nutrients move really, really, really small amounts in the soil, tiny amounts, and different nutrients move different distances. So if you think about what we're talking about as it relates to roots, right? Roots and placement have a big impact on the amount of nutrients that can diffuse into that plant. So the way we estimate diffusion, I hate to say it, but we don't really have a good way to calculate it. So what we say is you take mass flow, take root interception, subtract it from the total. That must be diffusion. That's really the best way to calculate it. But diffusion is very important for a lot of nutrients. So if you look at this graphic, you can see a bigger area for borates, sulfates, nitrates, chloride. But look at the area of uptake for all those other nutrients. It's very close to that root structure. Well, if that's the truth, which that is the truth, then how many roots we have, where those roots are, how thick those roots are, can have a huge impact on the uptake of those nutrients. So just sharing this with you, again, this is just to look at, say you look at the difference between mass flow, diffusion, root interception. Roots have obviously quite an impact on that uptake. So real quick, a root, as it grows, the business end of the root is the tip. So you get cells of differentiation close to the tip. They grow, they extend that root out. That root is covered with a compound called mucigel. It's slime for you Nickelodeon fans, all right? And the point of that is to help that root penetrate the soil. But if that root starts to encounter a soil density, right, it will change the physiology of that root. Here's the other thing, and I'm going to talk about soil density in a second, is to think about when we take a soil test, right, what do we do in the lab with that soil test? We put it in a blender and we grind it all up, right? We completely destroy the soil structure and any density changes in that soil sample. I read a paper about 4 years ago that said the actual gradient pathway, in other words, the ability of that nutrient to transport through the soil or the root to get to that nutrient, is 3 to 5 times more important than the actual fertility in your soils. And yet when we soil test, right, we destroy that gradient pathway, so it can lead to maybe some different results than we think we might see. So soil density is really important. And notice, by the way, I'm not talking about compaction. I'm talking about density here. So if we have and by the way, this is a little bit different from different soil types, sand, silt, clay. I'm going to generalize here. If you have a soil density less than 1.3, you're in good shape. You have a soil density less than 1.5, those roots are starting to encounter some issues. And once you get above 1.6 grams per centimeter cubed, roots will begin to turn. Okay? So what the root does as it starts growing through and it starts encountering these densities, I showed you that root and I showed you that area where the cells start to differentiate. They slow down the growth. They actually, in that root, the cell walls begin to stiffen. The root itself, those root cells get shorter and the root diameter begins to expand. It makes a thicker root in order to help that root penetrate through these areas of high density, okay? The problem, though, is that those forces, right, can really change the root morphology and restrict the nutrient uptake. So if you think about this density and density layers, they impact the plant in a couple different ways. So increasing bulk density actually increases root to soil contact. That makes sense because it gets tighter and tighter. And so it actually increases root to soil contact, but it decreases root length. And here's the other interesting thing. It actually increases oxygen depletion. So your soils, an ideal soil should have around 25% oxygen, 25% water, 45% mineral, and about 5% organic. That's the ideal soil. As root densities increase, we push oxygen out, and we increase actually the water in those areas of higher density. But here's the problem. When roots start to get in those areas of high density, they need 3 times the amount of oxygen in order to help load nutrients. But yet, when you look at this chart, that bottom line, it shows you that oxygen goes down when root densities go up. And that definitely impacts nutrient loading across that root, because oxygen is a key component to load nutrients across that root. So we've done some work up to this point on roots. Jason Gaheimer, our PFR manager, is going to come and share a little bit about some of the work we've done, and then we'll wrap up with some other discussion.
All right, so some of the preliminary work that we've done around root architecture has been with nitrogen, right? So we've actually done a lot of root architecture research, and we didn't know it, okay? Because we've been changing some of those things with nitrogen placement. So we started a trial 5 or 6 years ago where we wanted to look at putting nitrogen on both sides of the row. So how many of you apply nitrogen with your planter? Quite a few of you. How many of you do it on one side of the row? How many of you do it on both sides of the row? All right, more hands go up every year when we ask that question, right? So how many of you run closing wheels on your planter? How many of you run a closing wheel on one side of your planter? We run 2 closing wheels, right? For a reason. So it makes sense that we want to put nitrogen on both sides of that row. We want to get a nice, robust root mass. And when we think about things like closing wheels and hydraulic downforce and nitrogen placement, that's going to influence that root architecture. Jim talked a lot about preferential root growth, right? And so you can see here on your left, we have our control where we were just applying 30 units 2 by 2. Anybody know what side of that plant we probably put that nitrogen on? Pretty obvious, right? So then we take that same amount, that 30 units, and we just split it on both sides. You can see what it did to that root. And we see this time and time again when we dig roots in these studies. It's the same thing that we saw years ago when we were doing one aftermarket aggressive closing wheel with one solid rubber closing wheel. We'd see the same thing as that picture there on your left. We would know which side we put that more aggressive closing wheel on. Those roots would take that path of least resistance there. Okay, so you can see we've picked up 5.7 bushel by just splitting that nitrogen on both sides of the row. Okay, we didn't increase the nitrogen with that application, but then we did increase it up to 60. So we doubled now that we can add more nitrogen up front with that planter now that we're putting on both sides of the row, and we picked up another bushel and a half, bumping us up to 7 bushel gain compared to 30 units on one side. Now imagine if there's a lot of you who didn't raise your hands and said, I don't put nitrogen on with the planter. What if you're going from 0 nitrogen with the planter all the way up to 60 units, both sides of the row? What kind of gains we can be had there? This is actually some of the most consistent research that we have done over time. So we've done a lot of different trials in PFR, an exceptional amount around nitrogen. And this is one of the most consistent data sets that we have. Time in and out, we always see that benefit to put nitrogen on both sides of the row. So we've got a really big data set on nitrogen rate, especially corn after soybeans. So this is our new nitrogen rate study. We only have 2 years on this. But our old nitrogen rate trials, if you see the bar on the far left, 30 units 2 by 2, following back with side dress 160 for a total of 190. That has been our economic optimum nitrogen rate, okay? Not agronomic, economic optimum, 190. When we were doing 2 by 2, one side of the row, okay? So that's a 9-year data set showing that 190 was our economic optimum. So we started doing the research with 2 by 2 by 2. Do you think we're being a little more efficient with the nitrogen when we're doing that? Okay, so we decided, hey, let's start over with that nitrogen rate research, and we'll do 60 units 2 by 2 by 2, both sides of the row, and then we'll follow up with that V3 side dress for the remainders, okay? So we're doing 130 total, 160, 190, 220, 250, okay? And so for our 2-year multi-location data set, our economic optimum, now that we're front-loading a little more and we're placing it on both sides of the row, is now shifted to 160 as our economic optimum. So we're being more efficient with those dollars, with that nitrogen, as we're doing better placements, okay? So really exciting data set here that we're gonna continue probably for another 5-6 years. We're gonna look at it on different hybrids. And when I talk about looking at it on different hybrids, just take a quick minute, look at these roots here. Do you guys see any difference? Okay, there's a pretty big difference I want to point out on the 6296. So 6296 is a little bit of a smaller rooted hybrid to begin with. Its architecture is a little bit smaller than what we get out of 6374. Okay, so we've got a new study this year where we're looking at multiple hybrid types, okay, that we know have different root architecture. And what we're going to do is we got 3 treatments. We have a 2x2x2 treatment followed by remainder side dress at V3, Coulter side dress right down the center of the row. Okay. Then we've got another treatment that's pre-emerge. So we're putting that same 60 units on broadcast pre-emerge. So just kind of putting that nitrogen everywhere, right? We're not putting in a really good placement on both sides of the row with the planter. And then we're coming back with that side dress down the center of the row. The third treatment we have is we're doing the 2x2x2 placement, but then at our side dress, we're Y dropping, okay? So now we're putting all of our nitrogen with the planter and at side dress right on both sides of the row. And then we're doing on these different hybrids to see how that affects it. So you can see 6296, okay, big difference in what that root architecture now looks like, what that root looks like after applying 2x2x2 versus pre-emerge. We didn't see that big of a shift with 6374. Does that mean we're not going to see a yield gain? No, because we've tested 6374 doing these type of applications, and we see a benefit there. But will we get a bigger benefit on hybrids like 6296? Do we need to really make sure that we're focusing how we apply nitrogen or other nutrients to hybrids like 6296 and think about how we're applying those things differently depending on the hybrid and the root architecture that hybrid begins with? So a couple other things that we've learned, over the last couple years is what else could nitrogen placement such as 2x2x2 do to other characteristics throughout the plant?
Hello, everybody. Luke Schultz, Fiddle Grounds for Beck's Hybrids, and I'm at the London PFR site today and happen to notice a pretty cool observation within our starter fertilizer study. So in this study, we're evaluating 2x2, so a lot of nutrition, versus in furrow. Significantly less nutrition, but very efficiently because we're kind of baptizing that seed in it. So we're now 3 months removed from planning this study, because we're later July, and this study was planned on April 14th, and yet we're still seeing some differences, developmental differences. Results are still to be seen, obviously, at the end of the year. But here's how we know there's a developmental advantage in that 2x2 application, or that supply of concentrated nitrogen and sulfur safety in a 2x2 application. I'll first, though, point out the difference in how we know. These are the tassels, or specifically the anthers, of the in-furrow only application. And as you notice, as I point my camera up there, the vast majority, or at least 60 to 70% of those anthers that contain the pollen are still to be shed in the in-furrow only treatment, okay? Hopefully you can see that. But then when I move right over to the next row, 30 inches over, and I concentrate on that tassel, this is where we had 2x2. So we did not have in-furrow, but we had 2x2. We had 60 pounds of nitrogen. We had a little bit of sulfur in this application. But you can see the majority of those anthers have actually shed. That pollen has pretty well, pollination is pretty well commenced. And this is something we've seen all year long, particularly this year, because this year, we had a rather cool growing season. Crop maturation or development is kind of suppressed due to the cool temperatures throughout May, throughout June, and yet we can still see, at least developmentally, an advantage to that nitrogen and sulfur application concentrated in a 2x2 application right beside the row. So just something to consider. Look for the results this fall, but perhaps something to consider if you're thinking about perhaps trading planters, upgrading planters, making some planter adjustments. Something to keep in mind. Certainly, we don't see either of these applications paying every year as many inputs in agriculture do not. However, we do typically see a pretty consistent benefit when we can supply some nutrition, a significant amount of nutrition, I should say, in a.
So this is going to come as a shock to you all, but agriculture is changing, right? I know that's a shock, but a number of things are changing, right? Fertilizer prices, they vacillate, but they are going up. There's an interest in narrow rows. Why is there increased interest in narrow rows? I mean, you've heard of short corn, right? When they start talking about short corn, they're telling us to narrow our rows and or increase our population. That's important. banding, strip tilling. There are a lot of new technologies that are coming on the market that are allowing us to be more specific with how we place fertilizer. And then you guys have all heard carbon intensity, carbon sequestration. These things are changing the way that we do agriculture and the way we think about agriculture. In fact, because I'm an agronomist, I have to draw for a living. So here's what I'm going to say this. You guys can think maybe I'm crazy, and that's okay. Because here's the deal. We won't know the answer for 10 years, and by then I'll be retired. So you can write me or call me and tell me I'm wrong. But here's the deal. Today, I think most of you farm around 43,560 square feet per acre. I don't think you will in the future. I think maybe in the future, you'll farm, I don't know, 11,700 square feet per acre, or maybe you'll farm even less than that. And here's why I say that. Okay, if you think about where did I come up with that 11,700 square feet? Well, that's an 8-inch band, all right? And I'm going to draw in some corn plants here. And if you start thinking about new technologies that have come on the market, so think about some of the stuff that John Deere's brought up. Well, first of all, auto steer, right? And now autonomous auto steer. Our ability to stay on one path and, for instance, band our fertility, strip till, things like that has gone way up. What are some of the other new technologies that John Deere's released, for instance? And they're not the only ones. There's other companies that have these kinds of technologies. One is called See and Spray, right? So See and Spray and other companies have technologies like this. You'll have weeds, and you'll put your pre down, but then you may come back on your post, and instead of spraying 43,560 square feet, maybe you'll spray this weed and this weed and this weed, okay, and just kill them. And then there's other new technologies coming out. So John Deere released, for instance, the exact shot that's allowing us to place fertility right next to each and every seed. About a year and a half ago, I was with my son. So my youngest son, his job title is, he's a North American plant nutrition lead for John Deere. And we were riding together, and I said, Stephen, I got a question for you. I said, you know, today we're farming 43,560 square feet per acre, but if we can auto steer, and if I can spray individual plants, and I can put fertility right by the plant, why as it relates to fungicide, why don't I just start spraying a plant? Or if it relates to foliar nutrition, why am I spraying foliar nutrition out here in the middle of the road? Why don't I start spraying foliar nutrition and fungicide plant by plant by plant? And he didn't answer me. And I looked over at him, and he's smiling. And I said, you can't answer that question, can you? He goes, I can't answer that question, Dad. But what he's talking about, right, is where their thinking is going. And their thinking is going farming plant by plant by plant. Now, how did we have a learning around that? Well, it started in our 400 bushel plot. So we had a hybrid that hit 400 bushel, all right? And it did it, I'm going to say 2 years in a row, Jason. It kind of did it 2 years in a row. But here was the interesting thing about that hybrid, all right? We were told, don't ever plant that hybrid above, heck, it really was around 28,000 plants per acre. It won't respond. Interestingly enough, we were hitting 400 bushel between 36 and 42,000 with that hybrid. How are we doing that? They said don't plant it above 28,000. Here's how we did it. We did it by planting in 10-inch rows. And when we plant it, so let's say this is 30-inch rows here. In 30-inch rows, those plants are really close together. But when we went to 10-inch rows, we started spreading the plants row-to-row spacing out. And here's why that was so important. And our agronomist in northern Indiana is the one that figured that out, okay? The hybrid that we hit 400 bushel with very much had an umbrella root structure, okay? And here's one thing we know, right? I went and met with Dr. Belo at University of Illinois and asked him this question. I'm like, roots signal to each other, right? When roots touch, there's either it's a biosignal or a root exudate, but they signal to each other to say, oh, we're touching, we're a little bit crowded, we don't like this. And so they begin to respond when they touch and biosignal to each other. And Dr. Below said, yeah, absolutely. There is biosignaling that goes on. Here's what we think happened with 6622, that hybrid that hit 400 bushel. It very much had this umbrella root structure. When we were planting in 30-inch rows, we had a lot of that root touching and biosignaling that was probably telling that plant, I'm stressed, I'm crowded, I don't like it. And when we moved it into 10-inch rows, we gave that umbrella root structure the ability to express itself. And it completely changed the performance of that hybrid. So the question is, has anybody done any research to understand that? And the answer to that is yes. University of Illinois, a young man named Dr. Scott Foxhoven did years and years of research around this topic, trying to understand, does root size, he focused on size, impact a hybrid's performance? So let me ask you a question. What happens to corn roots as we increase populations? They go down, okay? They go down about 2.5% for every 1,000 plants we increase our population. 2.5% for every 1,000 plants we increase our population. They've done years of research there. They validated this by digging lots and lots of roots. Right, Sam? There's one of the PhD students from the University of Illinois. He's dug a lot of these roots, okay? And they're really confident to tell you that. Now think about this. What have we been doing with our corn populations the last 20 years? They've been going up about 400 plants per acre. So do the math. That means for the last 20 years, we've been decreasing our root size 1% every year. But think back earlier what I told you about roots and roots location relative to nutrition, right? Does that matter? It does. Now I'm going to zip through. This is about a 200 slide deck from Dr. Foxhoven. I'm going to hit some highlights that could really help you understand it a little bit better. So he looked at a number of hybrids, and he looked at their response to banding and broadcasting fertility, because his thought was root size can impact the response. So you'll see here, you see different responses to broadcasting and banding based on roots and hybrids. And we'll talk a little bit more about that. So that was one year. This is a separate year. And what I want you to really focus on is the trends, right? You see differences in the responses in the data. So this is a different year. This is 2019. And then they said, okay, why are we seeing these differences? What's mattering? Roots. One of the things that they theorized was it's the roots and what we're doing to the roots and the root size as we increase population relative to those responses. Okay, and does the original root size matter? Well, so I'm going to show you some more data. This is multi-hybrid research, okay? And what they did was they went in and they looked at population response versus fertility response. So you see kind of an inverse relationship to population and fertility, right? And then they started trying to say, what's the variable? What's impacting it? What's really changing this data? And what they really narrowed it down to was it's roots. The difference in the root type is really what's driving this. Now, I will also add, one of the things that we're interested in, and Jason brought this up, is not only root volume, but root architecture. Okay, we think root architecture may have an impact on these responses. So I'll show you one other study that they shared, okay, from their data. You could see that hybrids responded differently to not only population, but fertility as well. So you can see there, what I want you to focus on is the fact that the range of the responses. Look at the range of responses they were finding in their data. Well, why? Right? And this is what I'll just share kind of some of the final takeaways. One is that smaller roots, so think about this, smaller roots require better placement of fertility. Think back to that chart, that graph I showed you where it had the borates, sulfates, nitrates, and all those other ones. Smaller roots require better placement of fertility, right? This is my favorite. Rooting could explain some of the significant differences we're seeing as it relates to responses to population fertility. So I've been in the seed business a long time. I've sold and told and recommended hybrids to guys that I'm supremely confident in, and the next year they don't work. And I'm like, why didn't they work? I think, right, understanding roots and root architecture and root structure might help start answering those questions. And then a single hybrid's yield potential could be very different than what we thought based on root architecture, root size. And this is some of the conclusions from their data. But I think that middle one is really important. Craig Moore is our corn lead. Craig Moore has been digging roots for a long time. He really, as he thinks about architecture, he divides them up into 3 different classes: balanced, flat, and vertical. Here's some examples we dug this year, okay? On your left is a more vertical root architecture. In the middle, you can see the difference. It's very flat architecture, and this one is more balanced, okay? Here's an example of a hybrid that is flat. There's an example of a hybrid, very popular hybrid, very vertical. That's a picture of Dr. Foxhoven right there, and they dug lots and lots of roots. So the last 2 years, we've dug annually 300 to 600 roots, and we've taken them to the University of Illinois to have them scanned. And Sam, you call it a crop box. I still use the crib box, corn root imaging box, to look at what we can learn about 2 things in roots: root volume and root architecture. Then what we started to do was classify our products by that. So on your left is root angle. So if you're all the way over on the left, that's a very vertical root in that left graph. And on the right is more of a flat root architecture, root angle. And then root volume is the graph on the right. You can see there's some pretty dramatic differences. Then we started to classify them out and say, let's look at these roots by root angle, root volume. Across the x-axis is root volume. Across that y-axis is root angle. And I just picked out a hybrid that for us is a very consistent, stable hybrid, 6414. Has very vertical root structure and lower volume, interestingly enough. 2 days ago, Craig Moore, our corn lead, did a full-day analysis. He did a meta-analysis of 5 years of data, starting to look at, does root architecture matter as it relates to 3 things: population, stress tolerance, and nitrogen utilization. This fall, once we get 1 more year of data, we're going to release that data, but it's fascinating information. Last thing we did was we went and met with a gentleman at the Danforth Center in St. Louis, Missouri. He's doing a lot of work on understanding roots. He's got 26 people that work for him doing nothing but studying roots. They're really focused on genes, and genes that maybe confer stress tolerance in roots, or genes that confer nitrogen assimilation in roots. But if you look over on the right there, he showed us something he did with roots as it relates to growing roots. And we were fascinated by it, so we came back and we basically grabbed a bunch of old Kim totes, and we wrapped those Kim totes in shrink wrap. Then we put OSB around it, strapped it together, and we started fertilizing and watering. We put 1 plant in the middle of the Kim tote because we wanted to see if we could understand root architecture a little bit better. So we did that, and here's what we found. We'll show you these right now. When we unveiled these, when we did the first one, we're like, oh, that's interesting. That's pretty cool. But then when we did the second one, we were actually pretty stunned by what we saw. Because these are 2 different hybrids. This is 6414 on the right, 6485 on the left. Completely different root architectures. This one, all right, I would say a couple things. Very fine roots, massive amount of fine roots. Very vertical roots underneath that plant, directly underneath that plant, lots and lots of roots. 6485, completely different. 6485 has a high number of these, I'll call them node 3, node 4 roots, but I could park a basketball under that plant and not touch a root. It's a very umbrella root structure. Completely different root architecture. So let me ask you a question. If you banned your fertility, would that root architecture matter? Maybe. Not sure. That's what we're trying to understand. If you put these hybrids in different populations, does it matter? The data we looked at the other day says, actually, that umbrella root architecture, it's different. What if that one on the left, how does it perform in a poorly drained clay soil because it has more of those node 3 roots at the surface? Does it perform very differently than the one on the right? It actually does. So what we're trying to do, and by the way, when you look at them from the top, let's go back to our slide deck. When we look at them from the top, you can there's that. So you see on the left, that's the fine roots, the umbrella roots. Yep, I lost the slide. But when you think about moving forward, if populations are going to go up, if you're going to think about banding fertility, if you're going to place your fertility different, don't you think it's important for us to understand the interaction between nitrogen or fertility placement, stress, population, as it relates to your root architecture? Frankly, I think it's really, really critical to do that. Okay? That's why we've also collaborated with 2 projects this year with the University of Illinois to help us understand 2 things, that population interaction and then that nitrogen placement as it relates to root architecture. If I Y drop the one on the left, will I get a different response than the one on the right? We don't know. But here's what we really want to learn, right? We want to be able, think back to those 3 takeaways from Dr. Foxhoven's research, right? This may understand some of the variance we see in performance. So if we're going to make good recommendations to you moving forward, let's say I'm right about farming an 8-inch band or farming plant by plant by plant. Wouldn't it be good to know how the root architecture and root volume impacts your performance? Yeah, I think frankly as an industry, we've been a little bit derelict in understanding and studying to help you all succeed. I'm going to show you one more quick picture here. This is a root dig from Minnesota on Nate Furley's farm, and it's 2 different hybrids there. One is 5218 on the left, one is 5350 on the right. See, 2 completely different root architectures. Imagine I ban my fertility. Do you think I'm going to get different results? Probably. The 5350 has very much a vertical root structure. I would tell you, I think Nate's observation, Nate's standing in the back of the tent, I think Nate's observation would be that 5350 with that very vertical root structure seems to be handling stress a lot better. But it could also be that it will respond very differently to population and very differently to fertilizer placement. But we just have to understand that. And that's why we're doing these root boxes. That's why we're investing a lot in the future to understand how, if we can start understanding and phenotyping these roots, if we can just do 3 things, understand population, nitrogen, and stress response, we think we've really started to help our customers and farmers out there understand how to place their products better. Okay, so not only in roots, right, but in life, foundations are very, very important. So even the Bible teaches us that foundations are very critical to what we do. So as we move forward, what's next for us? We're going to continue to study, understand these things, these root architectures, root volume, so that down the road, we'll be consulting with you about this root architecture works really well in this poorly drained soil. And oh, by the way, this one responds very differently to banding of fertility. And oh, by the way, when you bump your populations up to 38,000, right, and we know that every 1,000 decreases root size, 2.5%, we need to start thinking differently about that hybrid. That's where we're trying to get to help you all succeed. So with that, appreciate you coming. You are free to come up and look at the root boxes. The 6485 on that side, 6414 on this side. Come look at them, enjoy it. Have a great rest of your day, folks. Thank you.
All right, well, welcome everybody. Glad you could come enjoy the air conditioning today as it started to warm up this afternoon. It's pretty comfortable in here. But I want to thank you all for coming. My name is Steve Gauck. I'm the Regional Agronomy Manager for Beck's. I've been with Beck's a little over 20 years. Lived down in southeast Indiana on our family farm. And I've had the opportunity to kind of be a seed advisor, agronomist now in this RAM role. And in this RAM role, I cover the east, so kind of Michigan down to Arkansas, so I get to see a lot of things. Well, today we're going to talk a little bit about feeding soybeans. And I'm excited that you're here, right? Because everybody loves to talk corn, but soybeans are just kind of that crop we have to plant in between corn crops for some of us, right? But there's a lot of things we're learning about soybeans, but ultimately, I know you all came here and you wanted to make this real simple, right? You are just looking for this product right here. The silver bullet, right? Spread that on the beans and it fixes all our problems. Which actually funny, this is actually a real product I found that they sell in gardening, and I just thought it was kind of hilarious, right? But I think about looking for this silver bullet, and we all want 100 bushel beans. But ultimately today, I hope I kind of help you think more differently about, hey, how do I take a 45 bushel bean field and make it a 65 or a 70, right? How do I increase these yields more consistently across my farm? But soybeans are kind of a challenge. When we think about corn, right, we can add nitrogen to it. We know what the reaction is. We add fungicide to it. We get a very consistent reaction. So it's kind of like training a dog. Give a dog a treat and it rolls over. The next time you give it a treat, right, it rolls over. You can train a dog. Well, soybeans, I kind of figure a little bit more like training a cat, right? You give it a treat, it might roll over. The next time it scratches you, the next time it runs away, right? Very inconsistent. And we see that with soybeans. But what have we learned through PFR that we can start to get some consistency and maybe we can train these soybeans? But first, let's take a step back and think about what are the factors that produce yield in soybeans? Well, here they are: light, water, and nutrients. Light being actually the most important. And that's what you came to hear about feeding soybeans, right, is light. But soybeans, right, well, obviously we use light to produce seed. So I want you to kind of think of yourselves not as a grain farmer, but as someone who is harvesting sunlight, and the reward for harvesting sunlight is the seeds that we harvest. So light is very important to soybeans, and actually soybeans are a terribly inefficient user of light. So we're going to touch on that. Don't have much control over it. Water, right? We can tile, we can irrigate, we can do things, right? Do rain dances, put a little extra in the offering plate, right? We can help with the water. Nutrients, we have a little control over too. And we'll focus a lot on nutrients today, but we're also going to talk a little bit about light. Now, here's the yield components of soybeans. So if we want to increase soybean yields, we need to know what part of the plant and how that plant works to produce yield. So it's all about plants per acre, nodes per acre. We're looking at pods per node or flowers per node, those seeds per pod and seed size. Can we affect and influence all these factors? So we're going to touch on some PFR data that shows us that. But first I'm going to start here, soil fertility. Now when you guys go to build a house, right, you all start with the roof and then you dig the basement, right? We don't do that. We got to start with that foundation. So in soybeans, that's fertility. So I asked kind of a crazy question. I go, do you fertilize for soybeans? And you're all like, oh, well, yeah, Steve, we fertilize for soybeans. Why would you ask that question? And then I asked this, do you fertilize before soybeans? And you all go, well, yeah, I mean, sometimes it's 2 years in front of the corn, but yeah, it's before I plant soybeans, right? Then I asked this question, right? You go to your ag retailer, and you go, all right, my goal here is to fertilize for 200 bushel corn and 60 bushel beans. And we're going to put that up 2 years in front of my corn, and we're going to go with that. All right, good. So you go out there and you raise 230 bushel corn, and you're out there showing this corn going, man, this is 230 bushel corn. Dang, I only fertilized for 200. I'm calling my ag retailer, and I'm getting a fertilizer buggy out here right now to take care of those extra 30 bushels so my beans don't suffer, right? We don't do that, do we? Okay? Or you go, nah, I fertilize in front of the beans, but again, you fertilize for 200 bushel corn, you raise 230. Are you making an adjustment to that soybean fertilizer plan based off that corn yield? Or are you just doing crop removals? Or do you just go, it'll be fine. Grandpa said soybeans are scavengers, it'll just be fine, right? It'll be all right. So ultimately, let's talk about this soil fertility. Here we're looking at 14 nutrients that are needed to grow a successful soybean crop. And over my career, right, we haven't focused on all these things. But when I actually started looking at this list, I thought it was interesting. I started looking at things like manganese, boron, molybdenum. I'm like, wow, we've been testing a lot of these things at PFR over the last few years. So it's exciting to see how we're looking at all these nutrients now in some shape or form in PFR. But if you would have given me a soil test and said, Steve, what do I need to do? I always start here, pH. pH is important, and I want you to look at this pH chart here on the right. And I want you to take a look where you see this block is as wide as it is. That means that nutrient's 100% available to that plant in the soil. Now, as this block narrows, that nutrient becomes less available. Even though it's in the soil, it's less available to the plant. So look at phosphorus up there, the second one. I'm at a pH of 6.5. I'm at the full-blown box. Phosphorus is available to that plant. I drop over here to 6. Look what happens. That block narrows dramatically. So you go, well, I put on 300 pounds of phosphorus, so I'm showing phosphorus deficiency. What's wrong? Well, the fertilizer's there, but the plant can't get to it because of pH. So ultimately, that's where I start. I got to have my pH right to release nutrients to be available for that plant, right? That's setting that foundation, getting it set right, making the right mix of concrete to get it going. Now, I throw up this 6.3 to 6.5, and you're going, wow, I cannot keep my fields between 6.3 and 6.5. And I don't expect you to. I threw it up there to get your attention a little bit. Soybeans actually react more to pH than corn. We can go lower than 6.3 and still raise really good corn. But soybeans like to be that 6.3 or higher. So if you're ready to do some liming this fall and you got fields going to corn, you got fields going to bean, target those fields going to soybeans first. You'll see a bigger reaction, a bigger payback. Now the 6.5 thing I actually put on there as a limit. Soybeans love pH higher than that. But if you're in a situation where you're fighting high soybean cyst nematode pressure, when we get above 6.5, they seem to be more active. Now we add Nemasect and other things to our soybean treatment to help with that. But it's kind of curious as you look at data, soybean cyst nematode pressure actually goes up when pH goes up. All right, so we're going to jump into phosphorus, and you're like, man, if I was in a corn talk, that would make sense. But people don't talk about phosphorus on soybeans. But phosphorus is actually critical to that life cycle of a soybean plant. And when we look at the list of just some of the things phosphorus does, you'll see photosynthesis is right at top. I told you harvesting light is extremely important to high-yield soybeans, so we got photosynthesis up there. We've got root growth, quality of grain, seedling vigor are all really important things that phosphorus does for us in a soybean crop. But I think this is interesting. I'm looking here at the uptake curve of phosphorus, and if you see, it's very steady all year long. So that plant needs phosphorus at a steady level all season long. Later, we're going to talk a little bit about how the soybean leaves store nutrients all year and then move them to the pod as we're filling. But the one nutrient it struggles to store is phosphorus. It doesn't build up a reserve, so it's got to pull that out of the soil all year long. Now, Dr. Fred Bilo at the University of Illinois, a lot of us know him for his work with high-yield corn and high-yield soybeans over the years. And this quote really caught me off guard. He said that soil fertility, particularly phosphorus, and a fungicide application are the most important management factors for increasing soybean yields. So when you walked in here, how many of you would have said phosphorus is the second or first most important thing to raising high-yield soybeans? None of us would have, right? I wouldn't have even until I started doing some research into this. It's really interesting how we're trying to increase yields with a nutrient, we use all the time in corn, but don't think about for soybeans. I actually did some more digging into this. I said, why? Why is phosphorus important? So what we're looking at here is a field that's below critical level on soil test, so it's really low on P and K. And we went in there and we took a strip and we added phosphorus to it. Well, we didn't really change the yield. We almost doubled the number of nodules. We did double the nodule green weight. So what are nodules, right? Nodules are extremely important to soybean production, right? That's where the nitrogen is produced. We want soybeans to have nodules and make their own nitrogen. Well, phosphorus had a big jump in nodule weight, number of nodules, but the biggest jump was the percent of nitrogen inside each one of those nodules. It improved that nodule's ability to produce some nitrogen. So then we took that same field, we took another strip, just put potassium on it. Because we all talk about beans love potassium, right? We need potassium. Well, the potassium by itself almost doubled yield, almost tripled the number of nodules, increased nodule weight, but did not change the percent of nitrogen much. So still we're producing more nitrogen because we made more nodules, but we're not producing as efficiently without that phosphorus. Throw them both together, yields double, everything goes up. So there's a synergy between the two. The potash is making more nodules, the phosphorus is making them more efficient. This was also interesting when I looked into phosphorus. This shows when a soybean plant needs and uptakes phosphorus. So actually, if we look at a 6-leaf soybean plant, a V6, only taking up about 9% of the phosphorus for the year. But if we go down here to pod fill, to mature seed, it takes up 44% of its total uptake during that time. Right? That phosphorus we usually put on pre-plant. We're here at the end of the season. What's happening during that time? Nodulation, which is the biggest stress on a soybean, is stopping. So that soybean's not putting energy into the roots. It's putting it all in this grain fill. How do we get phosphorus through the roots? And here we're looking at the biggest uptake time is when the roots are starting to shut down. So part of the reason then we talk about that is ultimately, sorry, I jumped a slide, is ultimately trying to figure out how do I have that phosphorus available all season. So if we look here at soil tests, so if I'm going to pull your soil test up, I'm looking at a critical level, and here I've got 20 parts per million. At 20 parts per million, right, if I'm below that, based on the tri-state standards, I'm losing yield. It's costing me money. Now, if I get above 40, adding fertilizer isn't necessarily increasing my yield enough to offset the cost. So that ideal range is between 20 and 40 parts per million on phosphorus. Now, we talk about going out and spreading fertilizer. We go to our ag retailer. A lot of us talk crop removal. Hey, I had 60 bushel beans. How much nutrient did I remove? Let's just replace it, which is fine. Removal rate of phosphorus in soybeans about 0.8 pounds per bushel. So if I raised 60 bushel beans, I removed about 90 pounds of MAP and about 100 pounds of DAP. Seems reasonable, right? But how much phosphorus does it actually take to grow the crop, though? That's different. So above ground nutrient, to create all that plant above the ground, it takes 1.07 pounds per bushel. So ultimately, that breaks down to 140 pounds of DAP and 123 pounds of MAP. That's how much fertilizer is needed to grow that soybean crop. Now, granted, if your soil test levels are good, you should be pulling some of that from the soil, right? But if your soil test levels are off and all you're doing is the removal rate, we're never going to get up to where we need to be of above ground. So let's talk potassium. All right? Potassium in soybeans. A lot of conversations over the years on that. It's vital to photosynthesis. Again, we go back to harvesting light. Photosynthesis is important. It's important in nodulation. We already showed that, the advantage of adding potassium at that point. Move sugars, okay? Potassium is a little bit like that interstate system within that plant, helps move nutrients around. Helps with a lot of stress, helps with a little cold damage. Thought that was interesting. And then it's about water use efficiency, opening stomates. So when you look at PFR proven, it's PFR proven to apply fungicides, foliar feeds in the morning when there's dew on. Why does that work? In the morning, that plant's relaxed, stomates are open, pulling those nutrients in. If I'm potassium deficient and they're closed, I'm not going to see the yield benefits out of it. So that's where potassium is really important. Here you see kind of the uptake curve. It's a little bit steep early in the season. But let's jump to soil test. These are based on the CEC, or the holding capacity of your soil. So if your CEC is below 5, your level's 100 to 130 parts per million. If it's above 5, it's 120 to 170. So these are actually the new tri-state fertilizer recommendations. But let's look at potassium. What does it remove? Well, 1.15 pounds per bushel. Okay? So if I grow 60 bushel beans, I'm taking off 115 pounds of OO60. Makes sense, right? But what about the above ground portion? What's it take to grow that plant and the seed? 2.37, nearly double. So I jump in there, I need 237 pounds of OO60 to grow 60 bushel beans. Takes a lot of potash. We got to have that potash available from that standpoint. So I'm not telling you need to spread 237 pounds because we're hoping to get some out of the soil. But if you're going for 100 bushel beans, right, potash could be a limiting factor. All right, we got our fertility set, so we've poured our foundation. We're ready to roll. Planting season comes around now. Let's go back through these yield components. We're going to kind of break them down. Can we do anything at each one of these stages? Is there PFR practices that show some advantages? So let's jump in here. Plants per acre. Yeah, a lot of you have seen this slide. I think this is interesting. 5-year data. This is 15-inch row beans. But we're looking at plants per acre. We're looking at May 15th and earlier. Planting before May 15th. This is planting May 15th and later. You'll see across there, I've got 100,000 seeds as my economic optimum seeding rate. Well, what does that mean? Well, what it means is you got to make a decision. Do you want to drive to the coffee shop and brag about your yields? Or do you want to drive there in a brand new pickup because you made the most money? Making the most money is the economic optimum seeding rate. Yield and making money don't always correlate, right? We can throw a lot of money at a crop. Now, I'm not telling you all to plant 100,000 either. But it's the fact of pulling those plants down, right? How many of you saw the news yesterday? New soybean yield world record out of Georgia, 206 bushels. What was his plant population? 77,000. You don't need plants to grow bushels, okay? And that's a challenge, though, because it's emotional, right? We want to see that nice green soybean field out there. Again, I'm not telling you to plant 100,000. 125,000 is only a buck or two off. If your planter's not set up, hydraulic downforce and closing wheels and all that stuff, yeah, we're probably closer in this 150 range. But I just want you to be thinking about more plants do not mean more yield. Now, when we jump into later planting, though, right, we're going to talk about nodes per acre. To get more nodes per acre, I actually have to have more plants out there because I'm not getting that growth. I'm not getting as much growth out of them when I plant later, so I got to have more plants for more nodes. This to me, though, is interesting because, man, I've always told, Grandpa always said, plant your corn first, right? Plant your corn first. But if you look here in April, we're at 100% of the mean yield in all our plots. Over 20, I think it's close to 24 years worth of data. 108%. May 15th, I'm still at 107. I get after May 15th. Look at the steep decline. You've probably seen talks here today that show the corn chart like this. It stays above 100% all the way through May. There's more of a penalty to planting soybeans late. There's still an advantage when we plant corn late. Some of that has to do with just the genetics in general, right? Corn genetics in general handle heat and can be planted later. But the penalty gets big as we start planting late soybeans. Why is that? Well, part of it is we want to canopy quickly to maximize light interception. We don't want any light hitting the dirt. We want that soybean taking all that light we can get. So we can limit weed emergence. We're going to limit competition. But this study from Iowa State really gets my attention. They were able to intercept 20% more sunlight, turn that into biomass, and they could double soybean yields up to about 60 bushels. So the key to raising high-yield soybeans is just harvest 20% more sunlight. Thanks for coming. It's not that easy, is it? But it really gets you thinking, right? How do I harvest more sunlight? I see a direct correlation to yield increase. So let's take a look here. Why sunlight? I got two plants here. And you think about a plant and you think about canopy, right? If I'm here and below, are these leaves getting any sunlight? Are they harvesting anything? Probably not, right? They're getting shaded by the ones on top. But look at this plant over here. See these petioles? They're going all the way up to that sunlight and coming all the way down to the base of that plant. I told you earlier that these leaves are like grain bins. So we're trying to store every nutrient we can in there, and then those nutrients move to here to feed those pods. So you say, okay, Steve, well, that's cool, but what's the difference between those two soybean plants? Well, our first one here on the left was planted at 200,000. It has 11 nodes on it. We're going to average about 3 pods per node, let's say. So that gives me 6.6 million pods per acre. Dang, that's a lot of pods, right? 6.6 million. Well, let's look at the plant on the right. It was planted at 110,000. It's got 26 nodes on it. A lot of that comes from the branching off to the side. If we average 3 again, we're getting 78 pods per plant. I'm getting almost 8.6 million pods. Nearly cut my population in half and added 2 million more pods. If you give me $2 million, right, I'll let you have the controller and we're done with the talk, right? 2 million's a lot. But by pulling that population down, letting that soybean plant compensate, we're able to add more yield. Now, this is also curious, right? We're still talking about this planting early and why the heck does it work? Well, we know June has the most daylight per day, right? On an average, the most daylight per day. And when I think about it, I go, well, summer solstice is June 21st. So the days start getting shorter after that. That's the end of the month. So July must be number 2. Well, if you actually look at data here from central Indiana, May has more sunlight hours in it than July. Now, only about 15 minutes worth. But think about it. If we're trying to harvest 20% more sunlight, which month do I need soybeans growing in? The number 2 month of the year that brings in sunlight. So again, we go back to this planting early. It's about the sunlight harvest, harvesting sunlight in May. It also does a couple other things for us, right? We're going to talk about that. But each plant, right, we're from first trifoliate up through R5. Amazingly enough, we're adding about a new node every 3.7 days. Okay, so planting early, that's a longer window, right? A 14 delay planting on average results in about 4 nodes lost. So May 1st to May 31st, I'm actually going to lose about 8 nodes. Now, I understand for some of us, where we farm, it's tough to plant early, right? Soils are wet, they're cold, I just can't get in there. But our challenge for our farm, what we try to do is always have that, we'll get that bean planter out and get it ready before that corn planter. We'll be rolling with beans as soon as that window breaks. Because we know beans can handle that temperature. We know they can come up uneven and still have a lot of yield potential. Okay? I'm willing to take that risk. Now, beans are more cold tolerant. They're definitely not more frost tolerant than corn, right? So there is that risk. But I know that if I get delayed, corn still has over 100% yield chance all the way through May. So I can actually delay my corn and still have a lot of potential. The other thing I think is interesting is the new genetics we have in soybeans. So today, soybeans, the new genetics flower earlier than the old ones. The old beans is, June 21st, summer solstice, we switch from vegetative to reproductive. That's the way beans are, right? Sunlight driven. But guys call me, go, I got flowers June 15th. What does that mean? And I go, it means yield, right? That's a good thing. If we can flower before summer solstice, there's a lot of yield potential. The other thing is that the R1 through R6 now last about 14 days longer. That's the grain fill period there at the end of that. We think about adding fungicide to corn when there's no disease. Why do we do it? We're trying to extend that grain fill period, make those kernels bigger. We know that increases yield. Trouble is, delayed planting takes away our advantages. Actually, they take it away to this point. May 1st to May 31st, this data here from Science for Success shows in Ohio and Indiana, it's about an 8% yield loss right off the top from being delayed planting. In Illinois, it's about 15%. Okay, so a month later, losing those nodes causes a yield loss. Now, this is what I think is interesting. When we plant earlier, we have a longer reproductive window because we hit that R1. There at June 1st, we can go longer. Now, what actually happens, though, is what I tell you. July and August have some good sunlight days. If I'm in R1 and going through that grain fill, I got more sunlight to harvest versus September and October, right? So if I want to extend grain fill on beans, it's about having more daylight available to extend that grain fill period. That's what planting early lets us do. It gives us better sunlight on the back end even. All right, let's go into kind of some PFR stuff then in terms of what can we do. Now we know our plants per acre. We know we need to plant early. What else can we do? Well, we talk about inoculants, right? Seed treatment or escalate's extremely important. We put a lot of time and effort into that. But as we jump here into inoculation, we think about inoculants, right? Why do we do it? Well, we're putting bacteria in the soil to help soybeans nodulate, right? We talked about nodulation's important. We're trying to produce nitrogen. We look here, we got 3 PFR proven products, not too bad. But in past history, we would think about, when do I use inoculant? Well, if that field hadn't been in soybeans in 2 or 3 years, I'd probably use it. It's coming out of pasture. It's coming out of hay. There's value to doing that. Well, my work in southern Indiana and enjoying the river, right, that would come out and flood the bayous, we would take all the oxygen out of the soil. Well, what lives when there's no oxygen? Nothing, right? So we're actually killing the bacteria. And then we go in and plant beans in those bayous as a replant, and they wouldn't nodulate. So in that scenario, we need to be inoculating to revive that soil. Southeast Indiana, we get in these wet, tight clays. You get over in Ohio, they get saturated, water sits. We take the oxygen out. What have we done? We've killed the bacteria. So that's where we'll see inoculation pay. These studies are done here on well-tiled soil in a corn bean rotation, and it's still working. Think about the jump in those scenarios from inoculant. Also, we think about inoculation, right, as we're trying to help that plant fix more nitrogen. On average, a soybean is going to produce about 100 pounds per year. Well, how many pounds of nitrogen does it take to grow a bushel of soybeans? It takes 4 to 5. So, all right, just put on 500 pounds of nitrogen, you can grow 100 bushel beans. All right, talk's over. Thanks for coming. We can't afford to do that, can we? But man, the plant's only producing about 100. Where's it getting the rest of it? Well, it's trying to take it out of the soil. But what if we can improve that? One way is through nodulation or inoculants, right? But the other is, some of you out here kind of scratching your head going, well, why couldn't I put a little nitrogen on beans? What would happen? Well, we looked into it in PFR. Now, over the years, we've done a lot of nitrogen studies on soybeans, especially down at Henderson. We've done urea and ammonium sulfate and Y-drop and weed and feed programs. And what we found over time was, once we got over 30 units of nitrogen, the beans got really lazy. Okay? They would go, well, there's free food here, so I'm not going to make any. So it'd be like if my wife brought home pizza, right, it's sitting on the counter, I'm probably going to eat it instead of making supper, right? That's what the soybeans are doing with the nitrogen. When we get over 30, they start thinking that. 30 must be more like an appetizer where they ate a little bit, but they're still hungry, maybe even hungrier, so they're going to cook supper. They're going to nodulate. So that's where we came up with this 30 units. Kentucky and Ohio, we're looking at a 2-year average, 30 units of 28, 2 gallons of ammonium thiosulfate, right? We're putting sulfur on with some nitrogen. Saw a nice return down there. 4 bushels, 2.7, almost $30 return. Well, that's got me kind of thinking, right? Again, we're putting this on in that 2x2x2 system, which has been very popular in the corn. So this looks good. Let's try it in some other spots. So we got Iowa, Nebraska, Minnesota down here in the bottom. I didn't hurt yield. I did increase it a touch, but I lost money. Well, that's strange. And we look at that and kind of go, all right, what's the difference here? Well, if we take Iowa and Minnesota, right, what do you think the average organic matter is out there? Woo, it's pretty good, isn't it? We'd all like to have a little bit of it. Okay, it's probably 5 plus. I look at Kentucky and Ohio, we're probably at 2.5 or less. Right, so organic matter, right, as it mineralizes, soils warm up, and there's moisture, what's it do? It releases nitrogen. So we're not getting that nitrogen release here in Kentucky and Ohio, but we are at these other locations. So the curiosity here in PFR is, over time, will there be an advantage to applying a little bit of nitrogen in our low organic matter soils to get these beans off to a big start? Now, somebody said, Steve, I am not going to put 2x2x2 on my planter. It was bad enough, it's expensive enough to put on my corn planter. I do love it, but I don't know if I love it that much. So we look at in-furrow. We've tested so many in-furrow products in PFR from a fertilizer standpoint on beans, and it is training the cat. They have been terribly inconsistent, okay? It's not that they don't work, but I can't get to figure out why or when or how. In this particular study here, you'll see there's an advantage to early planting. There's not to late. Goes back to mineralization. Now, I do think over time, though, we'll see more products become PFR-proven in-furrow for soybeans, but I'm not sure they're going to be all fertilizer-based or a pure fertilizer like this 624-6. But again, early planting in cool, wet soils, we did see an advantage. All right, now we're going to jump to nodes per acre. We got our plant set. How do I get more nodes per acre? Well, we already told you planting more plants doesn't necessarily get you more nodes per acre until we get mid-May and later. right? We start upping populations. But early planting, what do? Well, soybean actually averages about 20 nodes. But within those nodes, it has the ability to produce over 600 pods per plant. But on average, it only keeps 50 to 100. Okay? What are we going to do to keep those pods, right? Well, we're going to touch on that, but what about these nodes? This is also interesting. 70% of a soybeans plant yield comes from nodes 6 through 13. So it's kind of that middle part of the plant, 70% of the yield. So at R3, what's really interesting is the petioles and the leaves from the 6th node are all the way to the top. Still where sunlight can get them, you can get them with fungicide. And 13's at the top. So when we put on fungicide, we're actually protecting those nodes where our highest percent of yield comes from. That's why we think the R3 timing is so important on fungicide. So our optimum node number on June 21st, summer solstice, have 6 or more nodes out there. And you're going, well, Steve, my double crop beans, they're still in the bag on that date, so they don't have 6 nodes, but I can still raise good soybeans. And we can, right? I'm talking about that ideal situation. I want 18 to 20 nodes into flowering, right, which is R1, but I told you every 3.7 days we can add another node through R5. So if I'm at 20, everything I get on top of that's a bonus. Now, in the past, we always planted later maturing beans because we said, hey, they're more stress tolerant. They can handle the heat. They're going to put on more nodes, and that's true. But new genetics have really shortened that up a little bit. We don't see quite the node advantage. But if I'm in a high yield situation and I'm going after bushels on my good ground, I'm probably going to plant the longer maturing soybeans in my lineup on those fields. Now, we were looking for that silver bullet, right, on nodes per acre, and I looked through all kinds of research and PFR and everything, and I found it. It's planting early. It's that easy. More nodes per acre, you get them by planting early. Well, we all know that's not true, right? It's hard to do that. Difficult to do that sometimes. But we got to be in that mindset of pushing that planter. Also, a lot of that, it comes down to potassium. We do not want those soybeans to be struggling to get potassium. If they're healthy, they're happy, we can plant them early, we're going to maximize nodes per acre. Now, over the years, though, it's been interesting because I'd have customers call and go, my beans are chest high, they look beautiful. And I go, man, I hate to tell you, they're probably going to make about 40 bushel because the nodes are too far apart. All the 100 bushel beans I've been in on farms or PFR farms, they've never been over waist high on me. But what did they have the ability to do? They could slow vegetative growth and the nodes are about 1 inch apart. Okay? So over the years, we said, well, that's cool. Let's try to stack nodes. So we started doing that, right? Spray Cobra on them. Let's place Flex Star on them. Let's burn them and stun them. Well, we would stack nodes, but what happened? We burnt the leaves off, so we had no photosynthesis. We didn't harvest any sunlight. So it was very inconsistent, even though we did stack nodes. There's been some people looking at fertilizer burn. Maybe even loads of sulfur can stack nodes. That's got my curiosity up. We'll touch on that. Plant growth regulators, we're seeing some good results out of them, stacking some nodes, but we really see them paying out. We can add a micronutrient pack with them, right, to kind of offset all that and keep that plant healthy and happy. All right, now let's go through pods per node or flowers per node, right, at the end of the day. A soybean actually has the ability to produce over 1,000 flowers, but it aborts about 80% of them. That's a lot of work, right, to abort 80%. So we got thinking, well, what helps retain flowers? Well, lack of stress does, for one, but we don't always have control of that. But what else can help? Sugars, right? Those plants are producing sugars. Sugars can help retain flowers. So we looked at that in PFR. Here's some sugar products that we've tested. And then I pull up in the PFR book and I take a look at it and I go, all right, let's see if I can find some trends. I want to know why the sugars. What's going on here? Well, feed grade dextrose, I found out it's just corn sugar. That's all it is. So ultimately, right, I just had lunch and I ate ice cream cone. I should have had a Mountain Dew before I came in here so I don't fall asleep on y'all. Right? It's corn sugar. It's what we're trying to do. It's an energy boost. It's what feed grade dextrose is doing. It's cheap. It works. But let's look at these other products. All right, well, man, I don't know. What's similar there? Well, one is They all contain a sugar, but they don't contain the same sugar. So it's not the type of sugar. I got brown sugar, I got molasses, I got a mixture of sugars. They all contain a humic or a fulvic acid, right? Which are very similar products. They're an antioxidant, they help with stress, and they help get nutrients into the plant. So I'm like, well, that's the trend, right? I need sugar and I need a humic or a fulvic acid. That's the key. And I thought, it can't be that easy, right? So then I dug deeper. I started looking at another trend, the timing. Here, we're at R1. What's happening at R1 in a soybean plant? It's starting to flower. That's flowering, right? Well, wait a second. I got sugar, and I'm putting it on right at flowering. It's PFR proven all those products at that timing are sugars helping retain flowers. Sure does look that way, right? From a PFR standpoint, it all matches up. I thought that was a great trend. Well, that made sense. So then I said, well, let's look at the micronutrients. Let's look at all these foliar feeds, and let's see what's cool there from a trend. So I started going through them, and I'm like, what's in them, and what's my trend? Well, I look here, and I go, man, they're all over the board. I got macro, micro packs. I got fertilizer. I got nutrients, and then I got some that don't have either. And there's not a common trend here. So I dug deeper. Well, now I got these two products that are PFR proven at V4. They're actually some of the highest ROI products in the PFR book. And I looked at them and I said, okay, I got manganese and sulfur with a fulvic acid at V4. Well, that's neat. What's going on in a soybean plant at V4? Nothing. It's just growing, right? It's not setting any yield. It's not doing anything. A lot of us are probably making a herbicide application at that time, but nothing's happening. Or is there? Right? It's rapid growth setting nodes. And I told you earlier that fertilizer can sulfur help stack nodes. The two products that are sulfur and manganese with the fulvic acid are the ones at V4 causing a yield reaction, and a big one. Okay? So I thought, well, that all starting to add up, makes some sense. But what about the rest of them? So I started looking at the rest of these, and I'm looking at a big load of nutrients with fulvic acid, and the timing all fell at R1. So that got me thinking, well, all right, we're flowering at that point. I don't know if that affects flowering, but it got me thinking. My daughter used to run cross country. You're a cross country runner. What do you do the night before a meet or the day before a meet? Pasta, right? Carbs. You carb load so that at the next day then you have all that energy you've digested, you have those sugars to burn. Well, what are we getting ready to start after R1? Seed set and seed fill. So we're filling that plant full of all the nutrients it needs so it's happy and it's healthy at the start of the race when we're starting to put pods and seed fill. So that's kind of the trend that popped up there. Now, ultimately, if you could add one extra pod per plant, that's worth 2 bushels per acre. That don't seem like much, right? Just one. I just need one. That's pretty amazing, right? How do you lose pods per acre? We've talked about how do you gain them, how do you lose them? Late herbicide applications, burning off those flowers we cause the stress. Now, a lot of you look at that and go, I don't know. But think about this. I don't know if I'm fortunate or unfortunate. I was in the industry before Roundup soybeans. When everybody was non-GMO beans, there was a real big goal at the ag retailers. You never wanted to post-spray a soybean. That was a bad day. One, we didn't have products to do it. It caused burn, made everybody upset. So we did everything we could with pre-emergence and residuals to never spray post on soybeans. Then Roundup comes out and we're like, spray that weed, spray that. Everything dies, right? So why mess with these pre-emerge? Let's just spray. Okay, and then we go 5-10 years after, Roundup beans come out and guys go, wow, there's a yield drag. Well, is there a yield drag? Or were we spraying Roundup late, causing flower loss? So the reason I bring that up is there's an emotional thing to it, right? We don't like to see our beans weedy. Roundup helped us, create that issue. But also I want you to think about being heavy on pre-merge and layering residuals and trying to stay in front of that R1. Now, you're all going to have fields where you say, man, the weed pressure is going to cause more yield loss than me spraying late. Understand that. But I want you to start having that mindset of how do I get weeds under control before R1 so I can keep all my flowers. So seeds per pod, I got all excited. I'm like, I'm going to figure out how every plant can have all 5 bean pods. I could find nothing on how to make more beans per pod. And I thought this was interesting, right? So plants average about 2.5 beans per pod, okay? Seed fill begins at R4 and is done by R6. So that got me thinking a little bit, right? And we talk about corn, we're all about kernel depth and adding weight to it, and that's a lot of yield. What about soybeans? Well, root growth actually slows as seed growth begins. Nodulation, again, is the biggest stress on a soybean plant, so it shuts down nodulation to start filling beans. Shuts down nodulation, also takes a little bit out of the roots. But this is the point where I need 44% of my phosphorus into that plant, don't I? We talked about that earlier. How's it got to get in the plant? It's got to get there through the roots. This is why we all beg for late season rains to move that phosphorus to that plant to uptake for seed fill, to get those beans bigger, to add weight to them. We're actually doing some experimenting of how late in the season should we irrigate. All the leaves are off the beans, we're still throwing water at it to see if we can change this. So that's been interesting. But then I went back to the PFR book and I said, I wonder if there's anything that would affect seeds per pod or seed size. So I started digging. Well, here I found 2 PFR proven products and I looked at the timing. The timing is R3. Again, what's happening at R3? Well, nothing really, right? We're just setting pods, but we're getting ready for R4, which starts grain fill. So again, I'm thinking about how do I get this nutrient load to them? Well, we look at boron and moly. Those are the 2 products that are PFR proven at R3. What do? Well, boron helps move nutrients to that plant. Maybe you can think of it as a semi hauling grain from your farm to the elevator. So it's moving nutrients from those leaves down the petiole to those nodes. Moly kind of acts as a grease gun, helps move that better. Moly also helps with some nitrogen metabolization. So I told you we're quitting nodulation. I got to get all that nitrogen that's left and get it moving. Moly helps do that. And oh, by the way, we're making a fungicide pass at that time. Easy to throw in some boron and moly. Now, started looking more into the seed size thing. We talked about potassium, how vital it is to soybean production. So I got digging into PFR book again, and I think about PFR as interesting, right? Not everything works in PFR. And it shouldn't, right? Or we wouldn't need to be here. It'd be easy, okay? But this study caught my attention. We added a foliar K or a potassium acetate product at R3 again with our boron and moly and our fungicide. And every potassium product we added increased yield and had a positive return on investment. That doesn't happen very often in PFR. Now, granted, it's 1-year study, but this has got my curiosity up. I'm moving more of that potassium through that plant, right? It's that highway. It's opening up, moving nutrients. I got the boron in there, the moly, the fungicide. I'm more effectively moving all my nutrients into that plant right before seed fill starts. So I'm helping to increase seed size. So this is one I want you to watch. Another thing to really keep an eye on here, we've mentioned fulvic acid quite a bit. So we started just adding fulvic acid to things and see, wait, would it improve yield? Well, if you look here, we added fulvic acid to a product and we doubled yields. Now we went from 0.8 to 1.6, right? Not necessarily a big jump. Double yield sounds better, doesn't it? Okay? But we saw a consistent improvement. Here we're looking at 2 years, almost $12 by adding that fulvic acid, right? It's an antioxidant. It helps that plant from the standpoint of moving nutrients and getting nutrients into the plant. All right, so I'm going to kind of wrap up with this slide. And it's really busy. But what I thought was interesting, if you look at a fertility soybean book, and it says, here's the elements and their functions in soybean growth. And we look at boron. What is boron's function within the plant? Sugar transport. So we talked about the timing of boron and moving nutrients. That matches with our PFR results. Look at molybdenum. Nitrogen metabolization. Again, that goes along with the timing in our PFR studies. Potassium, enzyme activator, helps the plant withstand extreme temperatures and drought. Adding that foliar K, is that the coolest or the hottest time of the year? It's the hottest time of the year. So we're helping that plant through those stresses. So again, the phosphorus, crop maturity, seed production, when we get a late rain, we're seeing that. It was amazing to me how these functions matched up with our PFR results and the timing of certain nutrients. So I know that you were hoping finding that high yield soybeans was easy as finding this needle in the haystack, right? And it's not, but we're making that needle bigger and easier to find as we're looking at these results, and we can watch and see what PFR is showing us the timing of when and where. So ultimately, I want to thank you for coming. Appreciate your time. Glad you got to enjoy the air conditioning and enjoy the rest of the show.
My name is John Skinner. I'm a regional agronomy manager here at Beck. I cover Illinois and Iowa, and today my talk titled the Corn Soil Alliance is going to talk about corn and soil and the alliance they form. So by definition, an alliance is a union or association that's mutually beneficial to both parties. And that's what we're going to look at today. When I was setting up for this, I remembered a quote that I read in a book called The Round River about 5 years ago. And it said, if the land mechanism as a whole is good, then every part is good, whether we understand it or not. And that was a quote from Aldo Leopold, and he was kind of the father of conservation. He was a wildlife man. He observed a lot of nature. He was a philosopher, a writer. And basically what he was saying is, if our soil is healthy and good, the land, then every part of that ecosystem is going to be good, whether we understand it or not. And today we're going to talk about a lot of that or not portion. Because if we think about soil and corn roots and their interaction together, there's still a lot of things that we don't understand. There's billions of different species in that soil that are living. Bacteria, fungi, protozoa, nematodes, both good and bad. And we don't even have all those identified yet. So some of what we talk about today is going to be in that or not category. But back to the alliance. The two main characters in the alliance are the soil and the root, as I stated earlier. And when I told you the definition of the alliance, it was mutually beneficial for both parties involved. And so when I was thinking about this, I thought, well, this is kind of like a chicken or the egg scenario. Which came first, the chicken or the egg? Which one's more important to the other? Is the root more important to the soil, or is the soil going to be more beneficial to the root? And I don't know if there's any correct answer to that. But the first thing we'll talk about is the soil. And it's important that we understand the definition of soil, because we see it every day. We walk on it. We build things on it. And, it's kind of the foundation of everything we do in agriculture is that soil. But today we're going to focus primarily when we look at transfer and transformation of energy and matter, or the ability to support rooted plants. So we obviously know in farming we need it to support rooted plants, but we'll dive deeper into the transfer and transformations of energy and how that interacts with the soil and the root. Now, the other main character, the root, it's pretty complex as we think about it. So this is a cross-section of a root. So you take a root, dig it up, cut it in half, and look down it like you're looking down a drinking straw. And it's going to look something like this if you throw it under a microscope. Now, this picture is colored just to show contrast and detail here, but there's some key main parts. Around the outside is the epidermis. That's the skin. That's a protectant. That regulates flow of nutrients and energy into the actual physical root. That's the first boundary or first defense mechanism that the corn plant has. Inside of that is a spongy tissue area. This is called the cortex. Then there's another protective layer or membrane in here called the endodermis. It's an inside skin. Inside of that is all the xylem and phloem. All right? So in that xylem and phloem is the way we transfer nutrients and water through a corn plant. Xylem moves things up the plant, so from the root to the other tissues in the plant where we need those waters and nutrients. That process, movement through the xylem, does not require any energy by the plant. Basically, as the leaf goes through photosynthesis, that stomata opens and closes, exchanges oxygen for CO2, transpires water, evaporates. When that happens, it pulls nutrients up through the plant like a suction. The phloem, it requires the plant to expend energy to move nutrients or move carbon or amino acids through the plant. Every time you move through the phloem, you go through a series of plasma membranes, each one of those requiring energy to move it. Now, the phloem's interesting because it moves things both up and down the plant. When we move things down the plant, that's a product of photosynthesis. So that plant takes the nutrients in, captures the sunlight, goes through photosynthesis, sends stuff back down to the root in order to help that root grow and to feed the soil microbiology around it. So oftentimes when we look at roots, if I were to ask you what roots do, we'd probably get the answer, they take up water, they take up nutrients. But more importantly, it's what they give back to the soil. And that's what's illustrated on the screen right there. That's a root exudate. So that's a zoomed in picture of the mucigel that a root produces. It has a number of different functions for a corn plant. The first function that it has is to act as a lubrication method. So it lubricates the area around the soil so the root can push through, gain access to more nutrients, and continue to grow. The other thing is, through the process of photosynthesis and travel from the phloem back down, it's high in carbon. We all hear about carbon this, carbon that, capture carbon, sequester carbon. The root or the plant produces a high level of carbon on its own, and that's being used as a food source for those soil microbes. It's kind of a good old boys deal. The plant says, hey, I'll give you carbon, but you have to break down soil organic matter, things in the soil, and bring me back nutrients, either nitrogen, potassium, any of the 14 nutrients that the plant needs to grow. So the plant supplies the carbon, the microbes give the nutrients back, and that continues to cycle and cycle and cycle. It's also got amino acids in it, which we'll touch on those a little bit later. Now, I already talked about the take of the roots, right? They take up water, they take up nutrients. They feed any plant that we have in the soil. But it's not really that easy, right? They don't just take things up. We always talk about mass flow for things like nitrogen to the plant. It moves with soil water, it gets into the root, it goes into the plant uses it. It's really not that simple. We have to go through a few processes. So out here in the soil, move with mass flow or diffusion. The plant uses energy to draw nutrients into it. The nutrients come into the root through the epidermis. Once the nutrients come through the epidermis, they hang out here in this cortex. Okay? In that cortex, it's just full of nutrients, and that happens time and time again throughout the day. Then they need to make their way through the other internal membrane here called the endodermis. This is where it gets a little sketchy, okay? It's not like me or you going to an amusement park and we can just walk up, pick whatever turnstile we want to, go through and have fun. These nutrients, in order to cross that endodermis, have to have an active, what's called an active transport mechanism. It's something that basically reaches out into that cortex and says, hey, nitrogen, come with me, or hey, phosphorus, come with me. And each one of those active transport mechanisms can only move the nutrient they're assigned to. So if I'm an active transport mechanism, I can't go out into the crowd and get 5 of you different people and bring you all up here on stage. I can get 1 of you. That's all I can do is get 1 of you. Okay, so I illustrated it here. Think of that green bar there as that endodermis, that plasma membrane. All your nutrients are hanging out here in the cortex. They're all nitrogen, NO3, plant usable form. H2PO4, that's your phosphorus. K+, that's your potassium. Okay, they're all color coded because they all go to a certain active transport mechanism there. Once the plant signals that it needs more of whatever nutrient, that the active transport mechanism identifies those nutrients that are hanging out in the cortex, and it brings them across and groups it together. That plant then sends signals up from the root, signaling mechanisms to the root. The leaf or tissue, wherever these nutrients are designated to go, sends a signal back that says, hey, you got enough, stop. We don't need to take up any more. Okay? Once it signals to stop, we don't need any more nutrients. That's enough to do whatever plant function we're going to do today or in this hour-long span. They group together, they go into xylem transport, they go up into the plant. The whole process starts over. And this can happen hundreds or thousands of times a day, depending on the growing condition, depending on the amount of sunlight that the plant's getting, depending on how much energy reserves the plant is burning. This just continues to happen. Now, a lot of times in a real world scenario, folks will say, hey, I got nutrient deficiencies in my corn or in my soybeans, but I applied plenty of fertility. We've had plenty of rainfall and moisture to move nutrients into the plant. Why am I seeing these deficiencies? Well, it all has to do with the transportation and movement of these nutrients into the plant. For example, potassium. Potassium has over 70 of these different active transport mechanisms in the plant which move it. And each one of those mechanisms has a very specific movement chart. So it may move it from the root to the xylem, and that's all it does. And then there's a different active transport mechanism that moves it from the xylem to the leaf tissue, and from the leaf tissue wherever it needs to go. So if we interrupt any of those changes, development of those, or something happens within the plant where it can't have those active transport mechanisms, we can't move potassium where it needs to go. Okay? So that's why sometimes you'll see deficiencies knowing you've done everything right and supplied the plant with adequate fertility. The whole goal of this whole process and this whole alliance with the nutrient exchange and the carbon exchange in those root exudates is to influence the rhizosphere. The rhizosphere is that area right where the root and the soil interact the most. It's where all these nutrient and carbon exchange happens, and it's where microbial life is at its highest. The reason that's so important is because a lot of those microbial bodies in the soil have symbiotic relationships with that plant. And probably the most popular one out there is mycorrhiza fungi. That's what this is here. This is an exploded view of the rhizosphere, specifically the mycorrhiza fungi. So this portion here, the thicker, more prevalent portion, that's a root. These are all mycorrhiza fungi hyphae. That specific symbiotic fungal relationship is responsible for bringing about 80% of phosphorus into a corn plant. If that didn't happen, our roots would only give us about 20% of the phosphorus we need to have maximum yield and maximum crop growth. But when it forms this relationship with the mycorrhiza fungi, they fan out, they cover more soil surface area, and they get that phosphorus back into the plant. I'll give you an example. An acre of corn typically has about 34,000 miles of roots in it. Okay, so 1 acre of corn, 34,000 miles worth of roots. 1 acre of corn typically has about 1 million miles of mycorrhiza fungi hyphae in it. That's how important that relationship is. You go from being able to access nutrients over 34,000 miles to being able to access nutrients over 1 million miles. Doing this, improving that alliance, enhancing that rhizosphere, that's the biggest thing we're going to talk about today. There's 3 ways, in my opinion, that we can do it. In order to enhance that rhizosphere, where the corn roots feed the microbes use that energy to break down soil organic matter and give us nutrients from the soil back, you can enhance that in 3 ways. The first step would be to flood that zone with fertility. Apply fertilizer products that are going to make it so the microbes don't have to do that work, and new growth on corn plants or young corn plants can access those nutrients without expending much energy to try and increase yield. That's one option. Option 2 would be to feed those soil microbes that are in that rhizosphere. We're going to do things and apply things that are going to mimic those root exudates, those feed sources that the plant provides to them during this cycle. We can apply products that can mimic those, that are high in carbon and contain amino acids just like our root exudates do. The third option we have is to apply products that have microbiology in them or biologicals in them. So actual living strains of biology, or things like heat-killed bacteria or heat-killed fungi that are actual strains that can provide increased colony forming units, increased activity in these new strains that we add there. So adding something to the population that naturally occurs in our soil. Everything we're going to look at today and adding to the Alliance is going to be done from an in-furrow application standpoint. So the use of an in-furrow fertilizer application or adding these products in furrow. The reason I chose to talk about in-furrow is because if you don't have a liquid system on your planter, in-furrow is a cheap and easy way to get into that. You can do it for a couple, $300 a row unit. Add that to your planter. It takes a simple pump. All this stuff is low use rate, usually 5 to 6 gallons to the acre maximum. A lot of them are less than that. So it doesn't mess with your efficiencies. You don't have to outfit your tractor with a bunch of saddle tanks or things like that. And so with that being cheaper, easier to use, lower use rate, maintain efficiencies, that's where I wanted to focus on today. And at the end of this, we'll talk about a little bit of new technology in that in-furrow application space that's pretty cool. So, option 1 to influencing the rhizosphere was adding that fertility in furrow. So everything we look at today is going to be a PFR proven product. That means it's been tested for at least 3 years. It's been tested across multiple locations of our PFR farms. Every year we test it, it has a positive yield gain versus a control. And over that 3-year period, it's got a positive ROI. All these are PFR proven. So flooding that rhizosphere with fertility, making it available to young plants. Here's how we can do it. Pure grade diamond, 624-6. All our studies, we ran this at 5 gallons to the acre. It's 624-6, that's its analysis, so it's high in phosphorus. Phosphorus is something that we have trouble early season getting into the plant because a lot of the times the soil hasn't released that phosphorus to the plant yet. The soil microbial life hasn't been active enough to give us phosphorus. So high levels of phosphorus, 24% phosphorus by volume. It is low salt, so safe in furrow. It's 100% orthophosphate product. What that tells you is the second you put this into the soil, it's available for the plant to use. It doesn't have to go through any conversion process to be plant available. Looking at that product over 3 years, it's over an 8 bushel yield advantage average over those 3 years, and it's just under $13 an acre ROI in our pocket. Right, so there's a good option for you guys to use if you want to explore, flooding that rhizosphere with fertility. Nature's Impulse, it's 10-18-4, so another one that's heavy in phosphorus, 100% ortho again, so available to the plant. It's low salt. Then you look down here, it's got potassium acetate in it. So potassium acetate helps with the absorption of phosphorus into those young roots. Another phosphorus product we can look at, doesn't have an analysis, so not a true fertility product. This helps make phosphorus more available to the plant early in the season. So you run this at 1 gallon per ton of phosphorus applied in furrow at planting. Right? So making phosphorus more available through natural processes and not actually adding fertilizer, but mimicking what adding fertilizer does in furrow. You can see all these products up here have double-digit ROIs. I mean, the Nature's Impulse is close to $18 an acre and 9.5 bushel advantage on yield. That's pretty impressive for a product that we run at 5 gallons to the acre. It's also more impressive that you won't find a PFR farm in our system that lacks fertility. All right, these are high fertility acres. Most of them, El Paso, Colfax, Henderson, here, those sites are on good dirt. They got really good soils. So to see these kind of responses by adding these phosphorus products, it's influencing that rhizosphere. It's getting more nutrients in the plant earlier to help with yield. Step 2 was feed the microbes that are already there. Everything you see on the screen right now is doing just that. Now, what you'll notice about these is almost all of them have sugar. Feed grade dextrose, sugar. Exceed nano brown sugar, brown sugar. Centose FA, sugars and molasses. Molasses is just another form of sugar once you break it down. All these sugar products, everything that has sugar, it's all heavy carbon. It's all heavy carbon in those, and that's what those microbes are using to feed off of. They also have fulvic and humic acids in some of them. Okay, amino acids are the bases of those two acids there. So what these do is it's the best way we have to mimic those root exudates right now. Carbon, amino acids. Do it through sugar and fulvic acid. Now, when you look at feeding the microbial population that's already there, we don't see the same sort of yield results and ROI to the level we did at adding the fertility products. But what I will say here is these products are very cheap to use. So if they don't work on your farm, you're not out very much. Feed grade dextrose, for example, is 30 to 40 cents a pound. We run 4 pounds to the acre. All right, so you're out a couple bucks if it doesn't work for you. But we get 2.2 bushel yield response on it and $6.50 ROI. So you get a little yield boost there. You feed the microbes that are there. If it doesn't work on your soils, you're not out a whole lot. And that's pretty consistent for all these sugar products when we feed that rhizosphere, feed those microbes there. Okay? Step number 3, or option number 3, was add biological strains to the community that's already prevalent in your soils. 6 of them up there on the screen. All of them are very different. They all have some sort of biological strains in them. Some are live, some are not. Some have colony forming units, some don't. What I will tell you is on these, if you decide to try anything in that live biological arena or anything that adds strains of biology to your soils, start here. This isn't the gospel. It's not the only thing that works. But there's over 1,000 companies that are providing biological components or biological products to farmers. Of those 1,000 companies, there's about 10,000 different products on the market right now. So to sit down and go through all those labels or look at all the different options, that's going to take a lot of your time. It could get very expensive. Some of these products do come with a premium price tag on them. So what I would recommend doing is looking at one that fits your system. If it's a liquid that could go in furrow, that may work for you. If it's something like these Terracin products that can be got as a planter box additive that you apply just like you would your talc or graphite, maybe that fits more of what you're looking for. But if you find one and you find one that works, take a look at that label. See what strains of bacillus are in there. See what other humic or fulvic acids are in there. See what other live strains are in that product. See how many colony forming units, CFUs, that it has in it. Then you can build your program off of that. But just to start blindly pick one of the 10,000 out there may be a little difficult. I just wanted to provide these for you guys today to see that there are some out there that work. Now, the other difference within these, some of these have hundreds and hundreds of different strains of bacteria or fungi in them to try and benefit. Other ones, they work on single strain. They found one thing that they think works, and they're trying to perfect that single thing, like the methyllotrophic bacters in the Terracin. Other ones, they're throwing a bunch of darts at the wall and hoping something sticks. And they have in this instance. So however you decide to add to the Corn Soil Alliance to influence that rhizosphere, either flood fertility through in-furrow application, feed the microbes that are already there, or add new populations of microbes, I check this stuff out in the PFR book, page 38 to 42. That's where all this stuff comes from. Now, for a little more fun part here, one of one of the cool things we get to do as PFR is we get to collaborate with other manufacturers in the industry, other agricultural businesses. And this year we were fortunate to do a collaboration with John Deere. John Deere came out with a new way to apply in-furrow soil fertility, and it's through a system they call the Exact Shot. The Exact Shot system is over here on this stand, and what it is a high pressure injection nozzle that sits behind your gauge wheels and in front of your closing wheels. As you go through the field, it uses high pressure and shoots a squirt of fertility right down in that row. You can run that system on a constant, so it's applying just like you would with a seed firmer in furrow or just like you would with a furrow jet in furrow. But the real advantage that they got with this product over other in furrow application methods is the ability to dose fertility. And that's what we tested this year. So listen to this concept real quick. Every time a seed goes into the ground, this system can put a 2-inch band of fertility right on that seed. Then there's a gap to the next seed. Once that next seed hits, you get another 2-inch band of fertility all the way through the field. So what we're looking at doing is reducing our applied fertilizer rate drastically. If you're planting at 35,000 seeds per acre and you run a 2-inch band right on top of the seed and you do nothing in the gap than a 2-inch band, you come out at 1.9 gallons of applied fertility per acre. So cutting it by 2/3 right there. So you think of a product like 624-6, which we used in these trials, it's somewhere between $6 and $8 a gallon. We'll call it 7. 7 times 4, 28. You saved yourself $28 to the acre in application of fertility before you ever even ran the thing. Okay? So we set up these trials with John Deere. They needed us for the distribution market to test it, to actually get it implemented in fields. And myself and another gentleman by the name of Clayton Stufflebeam laid these trials out, and we ran the planter and the tractor itself. Here's an example of one of our trials to show you the scope in which we're doing this on. This field is at my house. It's 114 acres inside that gray boundary. This takes up a large majority. This one trial is over 70 acres. We've got 4 different rates in that. We got a continuous flow of 624-6, just like you would get with your seed firmer or furrow jet or other in-furrow application methods. We do what we call a dosed 1/3 6 gallon per acre. That's what I just described. It's a 2-inch band right on the seed. It's a 1/3 of the 6 gallon rate. So your seed's seeing the same amount of fertility it would if we were dragging it in furrow, but there's nothing in that gap. Okay, so you're using 1/3 of the 6 gallon rate. The next treatment we did there was no in-furrow application, just testing it with no in-furrow application. This strip right here is what I like to call our stupid strip. Okay, we mimicked a 12 gallon to the acre rate of 624-6. So our total application rate in this was 4 gallon to the acre, but we still put it on that 2-inch band that goes right over the seed. This gets pretty salty. It's a little hot. I don't recommend anybody doing it, but we did anyways. Okay. Cool thing about this farm is this half of the field over here is what's known as Oakville fine sand. It has about 110 to 120 bushel yield potential if it's not irrigated. You throw an irrigator on that, you grow 250 bushel corn fairly easily. The irrigator stops about right here. It's a pivot, goes around that way. You drop down 18 foot in elevation into a gumbo bottom. 5.5% organic matter down in this bottom, poorly drained, very wet, heavy soils. So we got sand on the top side that's irrigated. We got sand on the north side of the field that's not irrigated. We got some gumbo that's irrigated and some that's not. So we're going to break this down into 4 different management zones as we go forward. So we set all this stuff up and we said, so how are we gonna get this system to test it? And they said, oh, we'll give you the equipment to do it. So we're thinking, all right, we're gonna mount this up, throw a monitor in the tractor, mount this up to one of our PFR planters, and we'll do this. They said, no, we'll give you the equipment to do it. So they delivered this tractor to us, I believe it was April 10th, and they said, you guys can use this for a month to get your trials in. It's an 8R370 brand new tractor, 12 row 1775 high-speed planter from Deere. Outfitted with tracks, outfitted with notch closing wheels on it, automatic downforce on the fly. It had every bell and whistle on it. We planted all our trials with this. The unique thing about this is you think you're going to a planter applied fertility setup, you're going to need some bulk tanks somewhere, either on the tractor, on the frame of the planter, however you can carry that much fertility. With this dosing system, this is a real world example of all you need. The 250-gallon tank on that tractor. Okay? Doesn't add a whole bunch of frame weight, doesn't add a whole bunch of Pintro compaction or anything like that. Just a nice size 250-gallon tank right on the planter. So this will give you a pretty good look at how this system actually works. So it uses their brush belt delivery system. That's their high-speed system. All right, that's important because that brush keeps that seed right in place. It drops down that seed brush, it hits that eye, that triggers it to say, hey, algorithm, that seed's going to be there in this amount of time, we need a squirt. So it hits the furrow, squirt, squirt, all the way throughout the field. Just a brief comparison there to what it looks like versus a constant 6-gallon to the acre rate. But pretty impressive how it hits that seed every time. Now, if you look at the actual stuff doing the application, it's the same setup, the same solenoid, the same nozzle that you would see on the exact apply system on the sprayers that recognize a weed going through the field. They spray that and not areas where there's no weeds. Same setup, put in on a planter. This is just an example of efficiencies, right? If you're doing the dosing over here and only run a 2-gallon to the acre, you don't have to stop to fill up. You plant faster. That guy over there, he stopped twice to fill up. And then in the grand scheme of things, when it's all said and done, he stopped twice. He also ran a constant rate, so he used 1,200 gallon to the acre, 1,200 gallon total in a 200 acre field. This guy over here, he only used 400 gallon in a 200 acre field. So some savings that way. We'll see if it maintains yield. So I was skeptical of this thing at first, right? So you're going to tell me you're going to put this on a high-speed planter, and you're going to get a nozzle to shoot right down in the furrow and put a sewage band on that seed. And they said, yeah, we can do it. And I was skeptical. So we went up to the research farm in Cordova, Illinois, and we set the planter to 0 depth. Had no depth on it. They drove by 10 miles an hour. It laid a seed on the ground. It squirted that 2-inch band right on top of it. Next seed came, same thing. 10 mile an hour right through there. So visually we could see it work. And then I said, well, you know, that's good. It does it right on top of the ground. But what if we're hitting a furrow that's less than a 1/2 inch wide and you're going to do it? How's that row unit going to ride, you know, as we go through the field? And they said, you'll do it. It'll be no problem. You got active downforce on there. You can change that on the fly. It will change automatically as you go through the field. But look at 7 miles per hour. Look at the ride that row unit has. They got the beefed up parallel arms on there, and it just rides smooth. So didn't have any problem getting it into the furrow. So I was becoming less and less skeptical, and I finally said, well, if you got all that dust and all that debris kicking up, you're going to clog that nozzle. And they're like, nope, no problem. It's not going to clog that nozzle. So we ran that nozzle with the pressure on there between 60 and 70 psi. So it's pretty high pressure stuff. But you'll see here as we go through the field, we'll drop the planter in, we'll get off the end rows. Every time you see this nozzle squirt is going to be a seed coming out of that brush and into the furrow. We ran this thing over hundreds of acres. We did a 0 applied fertility test strip in the middle of our trials. All I had to do when I got done with that strip is hit the prime button. I watched every nozzle open up, clear itself out. Off we were to the next trial. So did a pretty good job. Now, I got a test stand over here, which I forgot to fill up, so bear with me for a second. This test stand is just like it would be if it was on a planter. So all the brains, all the guts, all the CPUs, everything that it takes to run your planter from an electrical standpoint is inside this box. So this is not just a vacuum and a meter, that's got power to it. This has all the components in you would need. So I'm gonna load it up with seed. Little white balls are perfectly round, they're very slick. The reason we have these little white balls is because it shows you how important it is to have that brush meter in there. So that brush meter, when you have a corn kernel that goes into it, it doesn't move. From when it gets delivered, set in the meter here, to that brush, all the way down, it doesn't move. And that's a huge component in making the accuracy of this nozzle be what it is. I got one more load to put in here. All right, we'll fire it up. It'll go through a cycle here, and you'll see it start delivering seed. It's delivering seed at 35,000 seeds per acre. So this is real world. This is how fast it delivers seed in the field. 35,000 seeds per acre. Constant 6 gallon to the acre rate there. So you can see it's always on. It's just applying. When we switch over, that's the dosing. That takes you from 6 gallon to the acre to 2 gallon to the acre, 35,000. If you guys were closer, if you want to come up afterward, you'll see that spray. It hits those little white balls, and it just shoves them down in the bottom of into my bin here. Okay, 35,000, 8 mile an hour. Does a pretty good job of hitting that seed, getting it where it needs to be. New in-furrow technology, they don't come around that often, but I'm pretty excited about it. I think there's opportunity here to not only have some pretty significant cost savings on your inputs, but as my brain thinks and I think forward, we don't know how important that fertility we run in furrow in the gap is in between the seeds. You don't really ever know if your plant takes that up or if it just uses what's right on the seed. So we'll see some of that. But I think if we can hit this, if Deere can engineer something to hit the seed, they can also give it an algorithm to say, don't hit the seed. So potentially applying something in furrow, but not on the seed, that may be beneficial. So when we look at things like boron, high levels of sulfur, higher rates of nitrogen, salty potassium products, we can't apply those to the seed safely. But if we could apply it in that gap and still have buffer away from that seed, maybe we'll get a kick on some of this stuff from the in-furrow side. I also think we could apply biologicals with this. If you look at those things that influence root growth and tissue growth or live strains of biological, if you could take your application rate and squirt it right there on the seed, the whole thing, and not have to drag that in furrow, that may be an option as well. So I think there's a lot of opportunity with a technology like this or other ones that come to market that are similar to this, that dose it in very close proximity to the seed. I think it'll be something cool to look at. So as I wrap up here, I want to remind you of the quote that I opened with. Is, if the land mechanism as a whole is good, then every part is good, whether we understand it or not. There's a lot we don't understand. I share with you all those options 3 of adding microbes. We don't understand what all those microbes do. We don't understand where they all come from. They're just present in the soil, and they do some stuff that seems to benefit our corn plants. And so we're still dealing in that understand it or not. But I didn't share the entire quote with you when I started. The second half of the quote is, to keep every cog and wheel in place is the first precaution of intelligent tinkering. And what he was trying to get by this is, and I'll relate it to my talk, is you can't just remove one factor from the equation and carry on and get maximum yields or maximum plant growth. So if we focus only on fertility and not the microbial part, we'll never have maximum yield. If we don't add fertility and we only focus on the microbial part, either adding them or feeding them, we're never going to get to where we want to be, never going to keep up on yield. So as you start to intelligently tinker with some of this stuff, add or change your operation, just remember to address every facet of that. Because if we move one cog or wheel, we're going to have poor results. With that said, I want to thank all you for coming today. I will be up here afterwards. So if you want to run the stand again, if you want to see that again, or if you have questions, please come up. I take questions, but with the air conditioner running, I can't hear anything up here. So Thank you again, and enjoy the rest of your day at Becknology Days.
Well, another season is underway, and we're grateful for it. I think we're all a little anxious what this year will bring, but we also have a renewed energy and a sense of excitement. We know there will be plenty of obstacles and circumstances we can't anticipate that will no doubt get in our way, which is why we ask for strength and guidance through the coming months.
We know this year will require sacrifices. And while we all may not feel like it's fair at times, we do know that we're blessed. Blessed to live and grow up on a farm. Those sacrifices and those moments we can't be together only make us more thankful for the moments when we are.
I don't do not busy very well, so learning to let go has been an adjustment. When I look back at my life, I know it wasn't the long nights or early mornings that were most important. The best parts of me have always been them, and I feel so proud watching them step in. I'm optimistic about the future of our farm, and I know they are ready. Please be with them and keep them safe. Amen.
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 Good afternoon. Great to see everybody here. I'm Scott Beck, and with me is my son, Corey. We're going to deliver the President's message today. So it's great that you all came, and I hope you're in this room for more than just to get out of the heat, all right? So when I watch that video, there's things that kind of come up within me in terms of what I see and feel. You know, certainly the young farmer, as he anticipates and looks forward to the new season with excitement and expectation, but also the sense of, not sure how this is all going to work out. We're going to encounter some things that we may not know how to deal with. And then the next scene with the mother and the young boy at baseball practice. And the husband's off and the father's off in the distance planting. And, in farming, I know growing up, I always tried to make all of my kids' games, but wasn't able to make all of them, and so there's those times when we just can't be together. And then the final scene, when the father is recognizing the work that he put in to his operation, the early mornings, the late nights, and then as he thought about it, it was like, that's not the most important thing. The most important thing is the kids that I've raised and what I see in that next generation and being confident and turning over responsibility to them. And so I can relate with all of those, and then our family can relate with, especially the third one, as my mom and dad are both here today. It's great to have them at Becknology Days, and it's great also that I could be here, and also with my son Corey, and I've got two other boys working in the business. And so I remember the confidence that my dad instilled in me 8 years ago. We were sitting in the boardroom and talking, and at the time he was CEO and president, and I was vice president. And he said, Scott, he said, what do you think about me retaining CEO position, but you being president? I said, I think that's a good idea. And so that level of confidence is what fathers do. They see in their kids, whether it's their son or their daughter, the capability and the passion and the drive, and they're willing to turn over those things. And that's part of life. It's a blessing to be in a family where we're able to see that transition. And so all you have come here today for something, right? Hopefully you've come curious and you've come with an expectation. And so we want you to think about what your next step might be, whether it's something like that in terms of transition in your family, or whether it's something you'll pick up from one of our tour speakers or agronomists or people talking about products and how you can make a change on your farm that actually improves the position and the profitability of your farm. And quite frankly, when you think about any change we make or any step, it really comes back to our belief and having confidence and believing that we can. And we don't always have that, but we also have people around us that can support us, hopefully, in taking those next steps. So I want to rewind back over 100 years ago and look at what we as an ag industry and farmers have done in terms of the tools that we've used to solve problems. And one of those tools is a plow. How many of you remember plowing? Anybody plowing today? Okay, well, we still do some, but I remember my grandfather telling me, how important it was for deep tillage, for weed control, even for controlling corn borers that next season and having every stalk turned over. And just like anything in life, when we use a tool that works for some things, we kind of tend to then start overusing it, right? And then it becomes a tool that creates problems. And that's exactly what happened with deep tillage. We had to start doing things different. Chemical companies came up with herbicides to help us to control weeds. Equipment companies came up with tillage equipment that left more residue on the top and allowed us to plant into no-till conditions. And those are the kind of advancements that we make. And I remember when I think about herbicides, as a kid, my dad said one day that we had a chemical rep stop by, and he dropped off a jug of this chemical that he said, if you just go put a drop or two on the leaf surface, in about 10 days to 2 weeks, it'll translocate to the roots and that plant will be dead. Thought, wow, that sounds pretty powerful. So I took the backpack sprayer, went out to the wheat field and put a little dose on each of the Canada thistle. 2 weeks later, they were smoked. You all know what I'm talking about, right? Roundup. And Roundup worked really well for a lot of farmers until it didn't work well, right? And so we had to rethink how we handle weed control. So our message to farmers has been really focus on your pre-applied herbicides. Do a good job early in the season. And we've got products like Liberty and other post-applied herbicides that work pretty well. As we think about the future, I think technology, particularly artificial intelligence, machine learning, cameras, and imagery are going to have a much more active role in helping us to use those tools even better. There's companies out there today that are helping us to deploy technology that allows us to detect a weed from a crop and to be able to spray a specific amount of herbicide just on that weed, not on anything else. And applying nutrients in the same way, I think, is a path for the future to help us continue to use these tools. So that's a little bit of a rewind in history of what changes we've had in agriculture. Corey, why don't you talk about some of the changes in our company?
Yeah, thanks, Dad. A lot of really interesting ag history there over the last 100 years or so, but I'm going to shift the conversation here for the next few minutes and talk a little bit of our family history and our company history. Now, the very first step then in our family actually happened when my great-great-grandfather, Lawrence Beck, purchased 80 acres just across the street. Now, his second step was to start cutting down trees because that 80 acres was not tillable. And so he had to prepare that 80 acres in order to provide a crop and provide for his family. Now, fast forward then about 3 decades, we get into 1937, and this was the first step for our family business. And this actually coincided with this new thing called hybrid seed corn, new development. And it was actually a partnership program with Purdue University that allowed any farmer to go and access 3 acres worth of this new thing called hybrid seed corn. So the start of our business was when my great-great-grandfather Lawrence and his son Francis each went up to Purdue and got their 3 acres worth of hybrid seed corn and came back and started Beck's Hybrids back in 1937 on 6 acres 86 years ago. Fast forward then a generation, now we're in the 1960s. There was quite a bit going on in our family and our business in the 1960s. So here's an aerial view of what the operation looked like at that point in time. Now, in 1962, that was when my grandparents, Sonny and Glenda Beck, were married. We actually celebrated their 60th wedding anniversary last year. 1964 then is when my grandpa Sonny came back to the family business, and he brought some new exciting ideas, things like practical farm research that you could learn about today. 1965 then, that was a really pivotal year. That was the year my dad was born. A few years after that came my Aunt Kim, and then even a few years after that came my Uncle Tony. So quite a bit going on in our family and the business in the 1960s. Go forward then to the turn of the century, 2001. Here's an aerial view of what the farm looked like at that point in time. And in 2001, we were actually putting the finishing touches on the brand new home office that you see across the street today. And I can actually remember a time when my dad took my mom and my brothers and I through the new office, through his office, when it was just steel beams. So that was a pretty fun experience for me. Now, in 2001, we were predominantly an Indiana company. We maybe sold a little bit of seed in a couple counties in the neighboring states, a little bit in Illinois, a little bit Kentucky, Ohio, Michigan, but we were really predominantly serving Indiana farmers. And we had 77 full-time employees at the time taking care of our customers. Now, today, here's an aerial view of what we look like from a bird's eye view, and that picture that I just showed, it cut off about right here. So we've got additional expansion in warehouses and soybean processing facilities, research and greenhouses that you see on this side of the street here. And so all that expansion and growth has allowed us to continue to serve farmers now in 15 states, and with over 970 employees to help us do that. Now, as we continue to grow and serve more farmers, an important part of that is our ability to provide the support and the infrastructure to serve those customers. So we were actually out in Goner, Nebraska earlier this month. We had the grand opening of our new site out there, did the ribbon cutting, and then we've got a few other expansions here coming down the line in the next few years with Salina, Kansas, Olivia, Minnesota, and New Madrid, Missouri. So again, expansion efforts to continue to help support our customers and the growth of our business. Now here's kind of a 30-year look back at what the growth of our business, has looked like. And if you'll notice, I was born way over here in 1994. So every year that I've been around, we've continued to grow and sell more and more seed. But if you get over here to 2022, what you'll notice, and if you were with us last year, is I shared with you that for the first time, that bar in 2022 represented over 10 million acres worth of Beck seed being planted. We've got another first to share with you today for 2023, and that is that we're the first family-owned, independently held seed company to have more than 2 million units of Beck seed corn planted in a single year. Now, what does that mean? 10 million acres of seed planted or 2 million units of corn, what does that really mean? Well, to me personally, that simply means that more and more farmers are trusting and believing that Beck's provides the best value per dollar spent. And as that trust and belief continues to grow, it also gives more farmers the freedom to understand what it means to quote the whole farm. So, Dad, why don't you share a little bit about what that means?
Sure. So how many President's Club members are in the room today? Planting 100% Becks. Okay, quite a big group. Any of you first-time visitors never planted a bag of Becks? Got a few. Okay. Well, when we think about how we think about customers, it's more than just about can we sell customers a bag of seed. Corey recognized the 2 million units that were planted in the U.S. But for us, it's much bigger than that. It's about how we can serve farmers beyond just the seed. And so Corey and I are going to talk about the whole package. But you won't get the whole package from us. We're just going to focus on about 4 of the things that we see that differentiate us in the customer experience. And what I would ask you, if you're whether you're a first-time visitor or you don't plant 100% Becks, what I would ask you to do today for yourself is before you leave, talk to one of our salespeople. Ask them to quote your whole farm. Now, you don't have to buy your whole farm from Beck's, but if you don't have that information, then I think you're doing yourself a disservice in understanding the total value that we can bring. So that's what I would ask you to do. Now, one of the areas that we're different in is the reward program. Now, if we were a publicly traded company, we would have outside investors, and we would want to return a dividend to those investors each year to reward them for their investment. With Beck's, our commitment reward program is kind of the way we do that. Because we don't have to reward outside investors, we can reward the farmers who are actually putting their dollars in our company, buying our seed. When we think about commitment rewards, more farmers are recognizing the value because they're thinking about it as a financial tool. It's a financial tool that helps Beck's customers that farmers who don't plant Beck's don't have that advantage. Now, if we look at just a little bit of a history, we're going to see how the number of farmers and seed orders going into commitment rewards is growing. The yellow bars represent the percent of our business in commitment rewards, whether it's a 1-year or a multi-year agreement. And over the past 5 years, that's grown from 81% to 86%, so about 1% a year on average. Now, the green bars represent an even bigger change. These are farmers who participate in a multi-year commitment. In 2019, it was less than 65%. In 2023, it was over 80%. So a 15% increase in farmers that are saying they're going to commit to a multi-year agreement. And again, I think it comes back to recognizing that it's a financial tool. It really helps beyond just what you might think about commitment rewards in terms of having tools or tractors or other items, toys in some cases. But people ask, how do we do this and why do we do this? Isn't it just a gimmick? Anybody heard that word used for commitment rewards? It's a gimmick. And I know if I was not a Beck's customer, one of the questions I would be asking is, well, wouldn't I be better off if just paying a lower price for my seed? I would honestly ask that question, and I'm sure some of you have as well. Well, I'm going to answer that very clearly and very emphatically today, that the answer is no. You're not better off. I wouldn't be better off. And here's why. Because you, as a farmer group, create value and you give us buying power. Collectively, you give us buying power to be able to go to a Case IH company or Ford or Chevy and say, we'd like you to quote on 100 of those trucks. Have any of you ever done that? You've gone to your Chevy or Ford dealer and say, I'd like a quote on 100 pickup trucks. Okay, so have any of you ever got a pickup truck through Beck's Commitment Rewards? Okay, quite a few of you. Well, in essence, you kind of did that. By placing your order, selecting a pickup truck, you gave us the power to be able to go to a Ford or a Chevy and ask for that 100 truck quote. And so that buying power really shows up then in the purchase price for what we can deliver it to you as. In other words, you get points for commitment rewards, and so there would be less points through our buying power. In other words, it would take you less points to get that piece of equipment than what it would take you if it was full priced. The second thing would be interest savings. So let's say you needed a truck or a piece of equipment, and you didn't have the money in the bank to go pay for that, so you'd have to go to your banker, right? You have to go to your banker, borrow the money, and pay that banker interest. So you get interest savings. The second thing on the list in terms of a financial tool is that when you look at your balance sheet, and let's say you had $90,000 in cash in the bank, and that shows up on your balance sheet. Well, if you needed a piece of equipment that cost $90,000 and you weren't in commitment rewards, then you'd take that $90,000 and go buy that equipment. It comes now back on your balance sheet as an asset, and so really there's no change. on your balance sheet. With commitment rewards, you don't have to spend that $90,000 on that piece of equipment. You get that piece of equipment through your seed purchase, and now you've just got $90,000 in cash that you kept in your bank account, and you've got that piece of equipment on your balance sheet. You just multiplied your working capital. That's how it's a financial tool working for your benefit, that collectively we're able to deliver more value. And then finally, there's tax considerations, and we just encourage you to talk with your accountant or your tax advisor to find out whether you should deduct expenses where you might pay for an item or just use the depreciation. So the last thing that I'll talk about is another program that we implemented 2 years ago to help us and to help our vendors to deliver you the products sooner that you want through commitment rewards. It's called Early Sign and Select. And this is when we simply ask you to sign up for commitment rewards, select the items you want by September 15th, and then we're going to give you an additional 5 points, which is worth over $1,800 in terms of things, what you can apply to getting your items. So Corey, why don't you come and talk about some of the things that you work on every day?
Yeah, so one of the areas of our business that we identified as a strategic capability several years ago was this idea of diverse product access. And this is a role that I get to play every day as I talk with our suppliers and strategic partners and trying to build out the most genetically diverse lineup available in the industry. And we know this is something that's important to farmers because there's data that suggests that every year more than 60% of farmers consider planting multiple brands. Now, I have the opportunity to interact with a lot of different farmers throughout the year, whether that's at events like today or maybe going and visiting some of our dealers or riding along with our seed advisors, or even farmers that come in just to visit our facility and tour and learn more about our business. So I get to interact with a lot of farmers, and I often ask them the question, why is it you might be considering planting multiple brands? And the answer is always two things. There's two answers. One is relationships, okay? My brother happens to sell for this company, or my uncle has worked for this company for years, or my best friend, sells for this brand. Well, that makes a lot of sense. People buy from people, and we want to support the people that we love and care about. So relationships absolutely make sense. But the second answer is always about risk, genetic diversity. I don't want to put all my eggs in one basket, because as you go from year to year, you don't necessarily know the challenges that you might experience. And so what we're able to deliver at Beck's is 100% of the genetic diversity that a farmer is looking for, all with one relationship. So we can access products from Corteva, from Bayer, from Syngenta, from our own proprietary breeding program, from all the other trait and genetic providers available in the industry, in order to deliver the genetic diversity that farmers are looking for. Now, another aspect of our business that's strategically and critically important is our Escalate seed treatment. And this was actually my first job when I came back to the family business a little over 5 years ago. And the goal with Escalate seed treatment is to provide the premium Cadillac option available in the industry. Because again, as you go from year to year, you don't know the challenge that you may experience. One year may be a heavy insect pressure year. The next year, it may be more disease pressure. And so our goal with Escalate is to provide you the tools to combat whatever challenges you may be facing year to year. Now, how are we able to do that? Well, we're able to build our Escalate package through something called our Escalate trials. And that is where we actually have 60 locations now throughout our 15 states marketing area where we will test different seed treatment packages. Now, right here, we'll test the Escalate package as it is today. Then right next to it, we'll test Escalate, but we may try a new insecticide in the mix. Right next to that, we may introduce a different biological. And then right next to that, maybe an entirely different package of ingredients. And so the goal with that is, again, to stay on the cutting edge of seed treatment options available in the industry. And so as you think about what we offer on seed treatment, we've got 14 modes of action on our corn treatment. We've got 8 modes of action in our standard soybean treatment. And if you happen to be in an area where there's heavy soybean cyst nematode pressure or sudden death syndrome, we also offer the iLevo and 2.0 upgraded package for an additional cost. But the base packages for both corn and soybeans come at no additional charge. So the goal is to deliver the most effective and premium product available in the industry at no additional charge. Now, there's another part of our business that comes at no additional charge as well, and that's our digital ag platform, FarmServer. So, Dad, why don't you share about that?
All right. FarmServer has about 9,000 users now, farmers that are signed up to use that digital ag platform, and 1,300 of them were new this past year, and I think that speaks of how more and more we're incorporating different things in FarmServer that farmers are finding useful. Now, one of the things that we've started to do is to integrate what we're learning in our practical farm research with the crop that's growing and being tracked in FarmServer. Here's a screenshot of what the FarmServer program looks like. And when you use FarmServer, it's pretty simple to go in and set up a field boundary, highlight the date that you planted that particular field with what crop and the maturity of that crop, and then the FarmServer program will build out a crop growth model letting you know approximately when the crop will hit different growth stages. So in this example, which you probably can't read, but I will point out certain things. Let's say we planted this crop on May 26th, and this green and yellow dot there represents, it says PFR, and that's at VT, or tassel time. So what we have done is integrated what we found in PFR research in terms of the optimum time to apply a fungicide is right around tassel time. So we would be sending you a notification for that particular field, for that product that you planted, saying that it's time to apply fungicide because that's given a positive return on investment in our PFR research. Now, one other area that we dove into this past year, we think it's going to help us as farmers to solve two problems that we typically make mistakes in each spring. Now, one of those is where we don't start planting soon enough, and the second one is we don't stop planting soon enough. Any of you guilty of that? All right, I've got my hand up as well. So we call this ready to plant. And the way the ready to plant program will work is each of these boxes here represents a day on the calendar. And the first day here, let's say that's April 15th. And it's 45 degrees outside. Soil temperature is 45 degrees. And let's say the soil conditions are optimum for planting. So how many of you, even with this forecast of 60 and 70 degrees for the next 3 days, looks to be, nice sunny days, how many of you are going to wait to plant on that next day? Any of you? How many of you are going to be a little bit more bold and say, I'm going to get that seed in the ground even though it's 45 degrees? I hope more people are raising their hand because that, I believe, is a key to getting better emergence because we're taking full advantage of those 3 days when it's sunny and 60 or 70. And so we're going to send a text message that says it's go time. And even though it's 45 degrees out, if soil conditions are right, get the seed out of the warehouse and into the ground. We think you're going to be better off in terms of getting that crop up. Now, on the other end, what happens when you've been planting, things are going well, it's 70 degrees, planter's running great, but the forecast doesn't look so good. It's 40 and rainy for the next 3 days and potentially heavy rains. How many of you are going to have the discipline to stop planting on that 70-degree day? Anybody? Well, we're going to send a text message that says press pause, because if you stop planting here when it's really nice, it might keep you from replanting 2 weeks later. So those are the types of notifications we want to send you to, help you get into this planting in a more optimum time. And actually, how many of you have a high-speed planter? Anybody? Isn't that a game changer? High-speed planters enable us to get more done in about half the time. And so what that means is we can get our crop planted more in the optimum window when it's going to be most likely to have strong emergence and early growth. Now, I want to change topics and talk a little bit about something that's been around for a while, but we've been hearing more about it lately: artificial intelligence and machine learning. one of the things that I guess artificial intelligence systems have been doing is they've been increasing in their ability to do what humans do in a shorter period of time. Here's an example, a very simple example of if human ability is represented by that top black line and time is represented on the bottom, the year 2000 up to 20 years later, the year 2020, and each of those colored lines represents a particular type of a test that was given to a artificial intelligent machine learning type system and how long it took that system to be capable of what a human is capable of. And you can see in the red and blue lines that it took those systems about 15 years to reach the capability of what humans can do. More recent tests, it only took a matter of a few years or maybe days for the artificial system to be capable of what of a human being in terms of taking that same test. So it's been happening for quite a few number of years, but it's happening at a much faster rate. Now, how many of you heard of something called ChatGPT? Raise your hand. How many of you have used ChatGPT? Okay, why do you use it? Why? Speed, okay? Speed of getting answers. Had one young man in one of the previous field shows, I asked, why do you use ChatGPT? And he said, to cheat. I listened to a podcast also where a freshman at Harvard University passed her freshman year using a ChatGPT type of a system, and she got a 3.5 GPA. So I think we've got some work to do in how we steward and police the use of this type of technology. Now, how many of you have no idea what ChatGPT is? Okay. Let me try to explain it this way. How many of you have done an internet search? Okay, so if you do an internet search, you're typing in, something you want information on. And an internet search is going to deliver back different websites you can go to, or videos, or other places where you can go look for that information. ChatGPT basically looks at the internet world for you and gives you an answer. So you don't have to go to those websites. It's going to deliver an answer very quickly. The adoption of this technology has been very rapid. In fact, it's happened much faster than any other social media platform. If you look at this graph, Netflix, there in the purple line, represents how many users or how long it took for Netflix to reach 100 million users. And you can see it took 9.5 years to get 100 million users. Twitter, Facebook, and Spotify, there in the middle, all took 5.5 years to get 100 million users. ChatGPT, there in the black line on the left, took a matter of days to have 100 million users. Now, a few weeks ago, I typed a question into ChatGPT. I said, what does Beck's research, practical farm research, say about fungicide applications on soybeans? Within a matter of seconds, it gave me this answer. I mean, just literally seconds. It searched our world of internet and came up with this answer. Now, the interesting thing is that it said that it didn't find any information specific to soybeans and fungicides in Beck's practical farm research. So it had a miss there. We got a lot of information on the internet about that. But it did say that it found information on our corn fungicide studies. And it gave more information on how to be effective in applying fungicides and how to steward those products. So the point being is, it is a tool. It does deliver information fast. Sometimes it gives you way more than you really want, and sometimes it doesn't give you complete information. And I've even read where sometimes it gives you wrong information. So you have to be aware of that. But it is a tool. So how are we as a company, beyond ChatGPT, utilizing machine learning and artificial intelligence? Well, we're using it very extensively in our research department. And we're using it to help our employees be more effective and deliver greater impact with the work that they do. So one example is this product that we created called Harvest Capture. Now, for years, one of the points of data that we've collected in our research plots, particularly in our plots where we're testing and developing our new genetics, is we need to measure plant and ear height. So our technology that we've used for decades is to have a person carrying a big measuring stick and another person carrying a clipboard and a pencil and going out to the field and walking through every plot and writing down plant and ear heights. Got the information, but not very efficiently. In fact, we only collected data on 1% of our plots. Through harvest capture, we were able to mount a camera on a combine, and so every plot we go through now, that camera is able to detect an ear and differentiate it from a leaf or the stalk, and then calculate what that ear height is. And so we're now gathering that information on 100% of our plots. Now, the next step is looking into kernel depth and how our combines can be the mechanism where we actually capture kernel depth on every plot. You see here this in the brown or in the square, that's grain that's laying against a clear plate in the combine. That's what that's a picture of. And some of those grains are laying flat against that surface, and some of them are laying on the edge. So we've colored the ones purple that are laying flat against the surface because those are the ones that we can try to measure the kernel depth on. So that's the work that we're doing. Hopefully that will deliver some good results. And we know how much kernel depth matters in any yield environment, whether it's low, medium, or high productive soils. And then one more area that we're digging into, literally, is exploring root depth, architecture, and mass. And one of the studies that our team did this year was that we took some chemical tote cages and we filled them with a soil-like substrate that allowed a corn plant's roots to grow basically uninhibited. So no compaction, they could grow freely through this substrate. And what I'm going to show you here is pretty impressive on the screen. Now, if you want to hear the full talk and all of what we're doing, then come to Jim Schwartz's talk and he'll unveil these baskets here on each side of the stage and you can see what that roots actually look like. But for the purpose of this talk, this is going to feel like you're walking into Jurassic Park of corn when you look at the size of these roots. Did you think a corn plant was capable of growing this large of a root system? It kind of surprised me. So our team is looking into root mass and root architecture to determine if it even makes a difference in a hybrid's ability to perform. Because we want to find out, if we have a hybrid that's got let's say a more vertically oriented root system, does it matter if we plant that hybrid in a low or a high population, or wide or narrow rows, or does it matter where we apply the fertilizer? Those are questions we have and things that our team is going to dig into so that we can deliver a different message in terms of how you can use each of our products. Because we want to be able to, through our learning and research, talk about our products differently to make a difference in your profitability. Because if we can help you see that, yes, this hybrid yielded really well this season, but in the type of management practices that you use, it might be better to have a different type of hybrid with a different root structure, because that might deliver more value at your particular operation. So our goal with all of this is to help you take that next step. And just as I mentioned, a father gives his son confidence to take that next step. We want to be here to support you and build your confidence in taking your next step. So Corey, why don't you take the final step here in the President's message and finish it out.
A lot of really interesting, intriguing information there related to digital agriculture and machine learning and artificial intelligence and both where we're at today and where we may be headed in the future. But I want to bring the conversation back here as we look to wrap up, back to your farm and to our farm, and why there's a reason to believe in the future and a reason to believe that you can take next steps. So it was about 5 years ago that my dad put together this A-frame structure. And what this is a reminder of the things that are most important to our business and how we show up and help serve farmers. Things like honoring God, helping others, and helping farmers succeed. Now, my dad didn't simply make these things up. These are really been fundamental aspects of our business for decades and decades and generations. But what he did do was take the time to put pen to paper and create this structure that allows us, as we go through our daily lives, to reflect back on how does this align with our mission? How does this align with our values and our purpose? Now, as we look to make different decisions in the future and where we may be headed and why there's reason to believe, there's a few things that I think are going to be really important for our business. One of them I mentioned earlier, and that's the idea of, as we continue to grow and support more and more farmers, our ability to invest in buildings and infrastructure and logistics to support that growth and maintain the customer service that farmers deliver and deserve, that's going to be really important. A second aspect of our business that I think is going to be important as we look to the future is our people. And today, I believe that's a competitive advantage for us. So our ability in the future to continue to attract and retain talented individuals who are committed to our purpose and our mission, who share an alignment in values and a desire to serve others, that's going to be really critical. Now, a third thing is an idea of innovation. And there was a really important person in our business who passed away about 13 years ago. His name was Lee Rulin. And he used to say, innovate, adapt, and overcome. And that attitude, that mindset existed then. I believe it exists today, and I believe it will need to exist in the future for us to continue to provide value to farmers. Now, as we're talking about next steps, my wife, Erica, and I, we've had an opportunity here over the last few months to watch a lot of next steps. We've got an 18-month-old daughter at home, and so we've been able to watch her go from crawling to walking to running. And in fact, last December, we had the chance to go up to a Purdue basketball game. And Blair, our daughter, having the personality that she does, she was the halftime show. They were hosting a baby crawling contest, and I thought I'd share that with you here this afternoon because I think it ties in really well with the concept that we're talking about of taking next steps. So take a look. All right, so I bet you can understand why that was so much fun for us. You know, she smoked those other babies. Now, if you have kids, you probably realize that you spend a lot of time teaching your kids things. And you also may realize that you can learn a thing or two from your kids. And so as I spent time here over the last few months reflecting on watching Blair grow up, I came to realize that we as humans, we find things that we're good at, and we oftentimes do more of those things. But sometimes the things that we're good at, they get in the way of us trying new things and taking next steps. And so as we think about that, and think about Blair as an example. So she was really good at crawling. I mean, she's responsible for the biggest blowout victory of Purdue's basketball season last year. But she's not crawling anymore. She doesn't crawl today. In fact, she was running around over here earlier. It can be difficult to take next steps. You may end up with some bruised knees and some scrapes. You may be confused and not know what the next step should be. But I want to encourage you that God doesn't design us to stay in the same place. We were designed to take next steps. And so as you think about your family or your farm, I want to encourage you to be confident, be courageous, and be willing to take next steps. Thank you for being with us today. God bless you. Safe travels home.